Uh, is my am I audible? Whoever is the host, am I audible?
So,
Hello, good morning.
yeah, good morning, everyone. So, I think I can see some maybe
Hello, good
yes,
morning. Can you hear me?
yeah, I can hear
Yeah,
you.
good.
Yes.
Good morning. Good morning.
Yeah, so I think the first session is over. Now we can, begin with this. So, formally, very good morning to all of you. And let me in the beginning explain that whomever we are seeing in this meeting, probably they are the one who have got entry through WebEx. But there are a lot of, participants, they will not get, direct access to this, but they are the one which are online visitor, and during the question answer session, they will join us. So it is my great pleasure to extend a warm welcome to all of you at Biosensors and Bioelectronics Symposium, ICEE 2020. I'm glad to see excellent participation of speakers and presenters. I wish you all a very enjoyable and very productive symposium. To begin with, in this first session, we have Professor J.P. Singh, who is a professor of physics. He is going to chair this session. And to give a very short introduction of Professor J.P. Singh, he is the professor in Department of Physics, IIT Delhi. He has, received his PhD degree from University Accelerator Center, New Delhi. He did his postdoctoral at Rensselaer Polytechnic Institute of New York, and his current area of research is Lansing angle deposition. He is also working on search-based biosensors. So I will hand over the charge to Professor J.P. Singh to conduct this first part of the symposium. Professor J.P. Singh.
Okay. Yeah. Thank you, Professor Prasad Mishra. So, for the kind introduction, and now let us this session, which is, I think, very one of the very important in this conference meeting. And so, right today we have our first invited lecture is going to be by Professor Soumya Mukherjee. So he's so Professor Mukherjee did his BTech from IIT Kharagpur in instrumentation, and then he did his PhD from biomedical engineering in University of North Carolina from USA, and currently he is chair professor in Department of Bioscience and Bioengineering, and so his current research interest is on sensors and instrumentation for wide scale development of resources, and like for environmental application, mobile health and security. And he has received several awards, and he has number of publications, and guided more than 30 doctoral students. So from this, like a very kind of a brief introduction, I just request Professor Soumya Mukherjee to present his research. Professor Mukherjee. So 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 the yeah, so just a brief, actually the timing is like
Hello.
if any question is. Yeah, we can hear you. Yes.
Yeah. Okay. So thank you, Professor Singh. Thank you, Professor Mishra, and of course, ICW organizers in this year of the pandemic. Of course, it is very difficult, and understandably, this might end up being less fun than an actual physical conference. But nevertheless, we got to do what we got to do and share our work with as many people as possible. I am not going to talk about really, very fundamental science or very breaking science of anything of that nature. My passion lies in slightly a different domain, which is using available technology to develop inexpensive sensors. We use optical fibers, we use paper and plastic substrates and all that. The optical fiber based work I'm going to present in the Photonics and Plasmonics Symposium tomorrow. But today I thought that we can present something on paper and plastic substrates, which can go into commercial use, not only because they're very inexpensive, but they also can be made very easily using very, very available resources, because that is one of the primary things that as a country, we do not have a high density of fabrication facilities, etc. So we need to make use of regular laboratories to make sensors which can be used and deployed and used. So I will essentially all the optical fiber work that we have done, or optical waveguide that we have the work that we have done, have been based on evanescent wave based sensors. And I do not think that I have to tell anyone what evanescent wave is, but just for the sake of completeness, I will say that the evanescent wave is sort of the power which is there outside the cladding of a waveguide, or outside the core of a waveguide. In a typical optical fiber, it is just outside the core, and of course, the picture that is shown here is very problematic because it has both ray optics as well as wave optics inside here, which is an anathema to physics professors. But I put that anyway, just to say that at every time there is a total internal reflection, there is some amount of power that is given by Maxwell's equations that goes into the cladding of the waveguide, or the outside the core of the waveguide, and that evanescent power can be modified by something which attaches to the core of the waveguide in sort of this format. Of course, the bottom side is completely wrong. The bottom side is showing that the evanescent wave is non-existent. That typically does not happen. That is an intentional thing to show that okay, that is something that really does not happen. However, that we have indeed a evanescent wave, and which gets modified by things which attach to the surface, like antibodies or antigens. Now, based on this, we developed a whole bunch of optical fibers, but and particularly by increasing the lower order modes to the higher order modes, by bending the fibers, we were able to increase the sensitivity of these sensors to a very large order. We could detect even down to 1 bacteria per mil, or which, of course, 1 bacteria per mil had a little issue with the results, because we tested over about 5 ml, and sometimes the results gave a let's say a normalized scale result of 1, sometimes it gave 2, sometimes it gave 3, but whatever, sometimes it gave 0.5. So there was a little bit of lack of reproducibility. We could use it for yes, no, but definitely not for quantification. But for 10 CFU per mil, we could do that reproducibly. And it is because of the bent optical fibers that we could do that. Now, this relied on a 280 nanometer wavelength of light that was passing through a solar resistant fiber, a solarization resistant fiber. But the source and the detector for this 280 nanometer is very expensive. So we actually started coating that with gold nanoparticles to use the evanescent wave to elicit a localized surface plasmon resonance. And that brought our sensor completely down into the visible range, visible light territory, where the source and the detector both became much less expensive. And we could detect down to 10 to 20 bacterial cells using these sort of probes. But these are all optical fibers. Now the thing is that the optical fibers are essentially fragile. These are, by the way, these are not 1 micron fibers or 2 micron fibers or 10 micron fibers. These are much thicker fibers. These are 200 micron fibers for that matter. But even then, they are quite fragile. Mass manufacturing might pose a little difficulty. It might be difficult for users in the field, although we have overcome that in some ways by using various cartridges. We know that thinner waveguides are very sensitive, but at that level of thinness, so to speak, the silicon dioxide fibers become really fragile, and that leads to more material wastage. So the question is that can we make waveguides out of polymers, and particularly if we can we make SU8? We started off with SU8 because SU8 we could make high aspect ratio structures. But SU8 does need clean room operations, so we also looked at PDMS waveguides and other types of waveguides which can be created outside of clean rooms. So this work is quite old for that matter. But what we did was take SU8 and make a U-bent waveguide out of it, and the black portion that you see, I hope my cursor can be seen. Can you see the pointer of the cursor?
Yes, visible.
Okay, so this black thing that you can see over here, this is essentially a microchannel. And so the waveguide actually forms the wall of the microchannel. So this was a very interesting design where we pass, if we pass analyze through this microchannel, they interact with the waveguide, and we can we can send in light through the end of the waveguide and pick up light from the other side of this waveguide, and we can make multiple of these on a wafer to make a multiplexed detection system. And it proved to be pretty useful. But then again, what we saw was that this U shape, where SU8 absorbs a lot of light, so this straight portion is actually quite useless. So instead of U, we converted that into a C, just this part, and launched the light right over at this edge, and took out light right over at this edge, thereby reducing the length of light that length of SU8 that the light passes through, and that proved to be much more sensitive as shown in this graph. Here we were using white LED and spectrophotometer and all of that. We could attach gold nanoparticles to the surface of the U-bent region and elicit localized surface plasmon resonance phenomenon over there, and that became quite useful for detecting extremely small refractive index changes, which typically happen during receptor analyte binding on the surface of the gold nanoparticles. We saw that the refractive index changes are much better if the response to the refractive index changes are much better if we coat the SU8 waveguide with gold nanoparticles as opposed to just having a bare SU8 waveguide. And when we applied that as used that as a biosensor, we could attach human immunoglobulin or anti-human immunoglobulin to the surface, and we could detect down to 0.15 micrograms per mil. Of course, this is not as sensitive device as many others which are there in the market, and for that matter, it is much less sensitive than many other sensors that we have made. But then also one has to think of this is made with very inexpensive material and is right there on the surface, and it quantifies as opposed to qualitatively detect yes or no sort of thing. One of the issues was that this SU8 waveguide was on one side there was of course free space or air, or whatever. The other side there was silicon dioxide. And now, if we look at the evanescent wave, how that goes, if we can remove the silicon dioxide from the bottom surface and we can use both the sides of the SU8 waveguide for detection, it might be actually better. So we tried to make the SU8 waveguide as a hanging waveguide of this nature. It was a reasonably simple procedure of doing this on a glass substrate. But right about that time, our SU8 started giving some problems, so we sort of moved away from it, and we started using what is called soft lithography. The soft lithography, the advantage is that once you make the master, you can make multiple structures using the master, and therefore potentially it becomes much less expensive. And soft lithography is typically where you stamp it or you transfer a pattern and things like that. What we did was essentially a sort of micro molding or a micro transfer printing, which we use for our purpose. and we use PDMS waveguides. We use PDMS as a material for this microtransfer printing. The master was, of course, fabricated using SU8 photoresist, and the beauty of it was that even if there are bubbles inside the SU8 structure, which was our problem that was happening at that point of time, it does not matter, because as long as the surface is reasonably smooth and well cured, it does a reasonably microtransfer print on the PDMS. The structure is backed up onto an acrylic sheet. Rapid curing, the mold is heated to 70 and in a hot air oven. After curing, the PDMS structures are carefully peeled off, resulting in something of this nature, where we have a hanging waveguide where we can send in the light at this point of time or point of space, take out the light over here, and we saw that the refractive index sensitivity of the PDMS based waveguides were far higher, 5 times more sensitive than the SU8 structures. The reason, of course, is because the PDMS has a refractive index which is much closer to that of water, and therefore even the slightest changes come out to be quite large. SU8 has a refractive index of more like 1.6 sort of thing, whereas PDMS has a refractive index of more like 1.4, which is much closer to that of water. So the slightest change in the around the waveguide creates a very significant change in the light that is propagated through it. Besides PDMS, the other things that we also tried out was use simple overhead projector sheets or PMMA sheets or ABS, which we use in our the 3D printers for development of these waveguides. The OHP sheets were typically cut into thin strips and bent in a hot air oven by putting it in a custom-made fixture. The PMMA sheets were also they were laser cut into thin strips and bent around the post, which gave it the forma, so to speak. And for the ABS, the filaments of ABS coming out of the nozzle of the 3D printer was taken and bent just like the PDMS to form these U-bend structures, as you can see from the figures here. This is from the using the PMMA. This is using the ABS, and this one is using the overhead projector sheets. And we tried to compare between these types of things in order to figure out what is going to be most suitable for us. There are for use of these things, a variety of cleaning procedures needed to take place, where they have to be cleaned with IPA, or in the case of OHP sheets, ethanol, and dried with DI water and so on, and then do for the OHP sheets, we can do a base piranha and a plasma generation of OH groups on the surface. And once the OH groups are there, we can put aminosilins on the surface, which generates amine groups to which various binding events can take place. Whereas for the PMMA and ABS, UV light exposure generated carboxyl groups, following which EDC and HS treatment gave rise to and dendrimers gave rise to the amine groups which are required for binding of antibodies or analytes. So this is a sort of optical setup. Obviously, I mean, some light is thrown in using a 600 micron optical fiber just to guide the light into these structures, and various tests were performed. We did a refractive analysis test, and as you can see, the best sensitivity to refractive index changes was got from the PMMA sheet, which was better than the ABS, and the ABS was better than the OHP and SU8, all of them. But later on, while using them, we found that the OHP sheets were somewhat better for using. That I'm going to come to in a couple of minutes. And we can always immobilize gold nanoparticles on this to use the LSPR phenomenon. And with the LSPR phenomenon also, not surprisingly, we saw that the PMMA had the most sensitive response, followed by ABS, followed by the OHP sheets. When we did the biosensing applications using using this PMMA waveguides, we saw that direct sensing was quite difficult. So we had to use the gold tagged analytes for detection, in which we could detect down to about 0.25 micrograms per mil of analytes, which was decent. It was not something which is fantastic or great, but it can be used in a lot of scenarios, again, simply because it is very, very inexpensive. We used the OHP waveguides for detection of myeloperoxidase. I'll come to what myeloperoxidase is in a later part of the presentation. It is an important cardiac prognostic marker, and we could detect myeloperoxidase down to about 100 or the nanograms per 100 200 nanograms per mil. So 112 nanomolars, so to speak. This the the advantage of the OHP sheet sort of thing is that it is even easier, even more easy to make than the PMMA or even the ABS sort of waveguides. Talking after that, so this is one part of the story where we are using very inexpensive polymer substrate for making optical type of sensors. The other part of the story is using paper and polymer composites or paper substrates, and on top of that some sort of polymer in order to make inexpensive sensors for a variety of. And we typically use electrical impedance spectroscopy for detection of these changes of these materials. The first thing that we had started off with is cardiac biomarkers. And cardiac biomarkers, as everyone is aware now, that there is myoglobin, troponin, and creatine kinase, where myoglobin comes out at the very earliest part of an infarction. But there is also another molecule called myeloperoxidase. Myeloperoxidase is a molecule which is expressed in the blood if there is endothelial disruption. And if there is endothelial disruption, that means that it does not necessarily mean that there is a cardiac event going on, but it tells you that there is a high possibility of a cardiac event happening, a cardiac or a cerebral event happening in the not too distant future. The MPO more than 100 nanograms per mil gives an important risk factor towards a cardiac or a cerebral event. We tried to detect myoglobin and myeloperoxidase, both of these things. It was done very simply. Just a Wattman filter paper was coated with polyaniline, and polyaniline acted as a passive capture device for the antibodies towards myeloperoxidase and myoglobin. And when the analyzed or MPO or myoglobin bound to those antibodies, it changed the charge density structure on the surface of the polyaniline, thereby changing the conductivity. And because of the nature of the substrate, it resulted in a impedance change which was primarily dominated by capacitive changes. As you can see from here, that it was coating the polyaniline on the filter paper created these clusters of polyaniline molecules over there. And we functionalized it very simply. It was just glutaraldehyde, DI wash. Glutaraldehyde creates imine groups on the surface of polyaniline, and then antibodies can be immobilized very easily on top of that. BSA for blocking the sites which were not reacted with antibodies, and then the interaction with protein. This is how it was carried out. This was published in IEEE Sensor Journal. Essentially, it is literally two silver lines drawn by hand, no sputter, no nothing. Two silver lines drawn by hand using a little template, of course, so that the lines are properly separated and uniformly separated in all the cases. And the sample was just dispensed in the area between the two electrodes, and that is it. And we could detect down to we could detect down to about 100 nanograms per mil of myeloperoxidase. So we are in that borderline. We could not detect down to 50 nanograms per mil. However, we could detect 100 and upwards. So that means that we can detect if there is a risk of the MPO of a cardiac or a cerebral dysfunction at some point of time. It could be detected in about 20 minutes. And non-specific responses were studied using a high amount of rabbit immunoglobulin, and the response was barely 4% higher than the baseline. So we don't even have to worry about that non-specific response towards other molecules. This was, of course, done in buffer, but now the moment that we put serum in it, the detection limit was had changed simply because the availability of the other proteins and albumin in the serum. This is something that we are trying to overcome by doing various types of blocking and making the systems more of monoclonal antibodies and stuff like that. We did detect it, improve the detection limit to 500 nanograms per mil from that 1 micrograms per mil by blocking the surface with human serum prior to applying the spike sample. So use a normal human serum to block the unreacted sites and then use the sample serum actually. It did improve it, but there are much more scopes for improvement in this regard. The other aspect of these paper and polyaniline or paper and polypyrrole sensors is that one can make very easy disposable taste sensors. And as you know, taste or smell is not typically the sensors are multiple sensors on which the reaction of the analyzed species or multiple species produce different fingerprints for the different sensors. We use principal component analysis for analyzing these. We used doped and dedoped polyaniline and doped and dedoped polypyrrole for the 4 sensor dots, as we say. And these 4 sensor dots were dipped in a solution, and we tried to detect the 4 primary tastes, which is sweet, sour, umami, and salt. And they indeed, one could see that the impedance responses were different for the various tastes. And once one does particularly a principal component analysis, we can see that they are very well separated in the principal PCA space, and the sucrose is way over on one side. The other ones can be explained on the basis of certain ions or protons and things like that. The sucrose is a little bit more complicated to explain as to how it appears so far away and what are the reactions of sucrose with polyaniline or polypyrrole. We also try to distinguish, you go to you take a bottle of water, buy a bottle of water, you really don't know whether someone has just given you tap water or someone has given you really pure water. We did a PCF to differentiate water from different sources, and we could see that we can even use that to distinguish whether some corrupt person is just bottling the water from a tap and selling it as high quality purified water or something like that. So that can be distinguished using this PCA and these sensor groups. Also, we could detect between various brands of orange juice and whether the orange juice had any added sucrose to it. Fresh orange juice was made in the lab without adding any sugar to it, and that was very different from the typical orange juice that we get in the market as under trade names of Real or Tropicana or things like that. We can use this for the detection of breath alcohol. We can use this for detection of breath acetone. We have done that. Patents have been filed for doing that. We can make more sensor dots for detection of noxious gases in industrial environments. We can detect explosive vapors also possibly using this sort of a sensor dot combination using a very simple PCA, which can even be ported onto a mobile phone for the analysis purposes. The last little bit that I want to talk about here is again using a paper-based sensor and with polyaniline, and on the surface of it we immobilize bacteria or virus, and then use chitosan silver nanoparticle composite to look at the response of the bacteria or the virus to this. Now, what happens is the bacteria which gets bound to the surface of this polyaniline, because the polyaniline has been functionalized so that the bacteria or the virus comes and attaches to it, the bacteria in the presence of silver nanoparticles, they lyse. I'll just take another 2 minutes. The silver nanoparticles, they completely lyse off. Whereas the virus, they sort of aggregate, and that produces very different impedance signatures for these two. As a result, now we have developed a sensor, a single sensor by which we can distinguish between bacteria and virus, and we can actually distinguish between a purely bacterial sample or a purely viral sample and even a mix. This is significant because very frequently, when you go to the doctor with some cough or cold or something like that, the doctor does not necessarily know whether it is a viral disease or a virus plus opportunistic bacterial disease. If there is an opportunistic bacteria, it makes sense to give antibiotics. If it is a purely viral, there is no point in giving antibiotics. As a result, when they give antibiotics without proper reasoning, without proper proof that there is some bacterial infestation, this antibiotic overuse has resulted in antimicrobial resistance, which is a big problem in the world right now. So with this thing, we can have a point of care sensor which can distinguish between a purely viral sample, a bacterial plus viral mix, or a purely bacterial sample. This is the importance of this thing. It has gotten recently published, and of course patents and other things have been submitted. At the end of this, I'd really like to acknowledge the funding agencies. There are lots of funding has come from various things for little things all over: DBT, DSP, ICMR, Ministry of Information Technology, Tata Trust. The students, Dr. Nirmal Punjabi, Dr. Anjali Khatri, Devasrita Mandal, and Aswati, Kapil, Pooja, Saurav, many others. And my collaborators, Professor Suparna Mukherjee, Professor Kundu, Professor Mariam Sujai, Professor Devjani Pal, and to some extent Professor Ramgopal Rao, and many others. Thank you very much.
Okay, thank you for Professor Mukherjee for such a wonderful talk, and then you really did it well in time also. That is great. So yeah, so now the dice is open for questions. If you have any, please ask. So any participants wants to ask any question or any query if you have?
I don't know whether the participants can ask because they are disabled from asking, I think. They have to put it in the chat box or something. I don't know.
Yeah, I was checking the chat box, but I cannot see any comment. But anyway, I have, meantime, I have one like a little bit query. So if you can,
Please.
so yeah, so yeah, really, I like that work. Like you use that plastic and that paper substrates for detection. So I'm just wondering, have you tested? Have you checked any kind of a mechanical? Have you done any mechanical test on the like kind of flexibility or the long term like uses of your like aging effect on your substrate? Like any mechanical test?
You see, all of these are single-use sensors. So the aging of these plastics, of course, polymers do age, but they age primarily in response to exposure to the environment. And since these are going to be single-use, it is unlikely that we have to do a long-term aging effect or the mechanical property change effect of these. However, it is definitely true that If we have, when we are bending these polymers, ABS is a little bit more fragile than the other two for that matter. While bending it, the OHP sheets are remarkably stable. Nothing happens to them while we bend it. The ABS is slightly more fragile in bending. So it is while the bending takes place, that is when the most of the mechanical issues come up.
Okay. Okay, that's great. Another thing is one I just had my query. It's like that was also really interesting. Like at the some like your final slides, maybe you have shown about the you can distinguish between basically the pure viral and pure bacterial samples. So my query is like, what is the basis of like that difference? Actual like why this actually physically the impedance you see the change? I
Yeah.
can see the results are good, but what is the
What is
basic?
the physical basis? Yeah, the good question.
Yeah,
I mean, that I alluded to that, but because there's no time, I did not really expand on
yeah.
it. Chitosan silver nanoparticles, they typically silver nanoparticles lyse the bacteria. So when they lyse the bacteria, the internal things come out, and they essentially the space near the sensor surface, they get filled with electrolyte. Okay, so as a result, you can see a negative change in impedance when the chitosan silver nanoparticles is applied on the surface of the bacteria when there is bacteria in it. But when there is a virus in it, if we apply the chitosan nanoparticles, they actually don't lyse the virus. Rather, the virus sort of aggregates with them. Okay, so that aggregation leads to a change in impedance on the other side because the chitosan adds on to the impedance of the story.
Okay.
So that is how that is a mechanistic explanation to what is happening. We have ACMs and other pictures to actually show. I don't know whether I have it here. Yeah, there is actually. As you can see that with the chitosan and all that, these viruses actually aggregate very well around these nanoparticles, and that gives rise to the positive change in the impedance.
Okay, so there are two questions from the participants. I can check on the chat box. So first one is by Dr. Tripathi. He is asking, can we use these PANI sensors for viral sample detection from blood as a diagnosis method?
Uh, uh, right now, we have not tested it, but yes, I mean, theoretically, of course, it is possible. We might have to clean it up somehow, but I mean, that is something that we would like to do. We have not yet done it. We hope that this can be done.
Okay.
But definitely it can be done in saliva and other things. So we have proposed this as one of the methods for detection of COVID in saliva.
Yeah. So second question is like regarding the minimum limit of detection. How you decide the? He's asking how Dr. Singh, Mr. Mukul Singh is asking how to decide minimum limit of detection. So that is.
So there are two ways that we decide on the limit of detection. Number one is up to what is the lowest amount we can physically detect. However, the response of the sensor must be at least 3 times the baseline noise value of a control sample. So if you have a control where there is no analyze and it has some sort of a noise or some sort of flickering, the 3 times of the amplitude of that noise, the LOD or the limit of detection can only be beyond 3 times of that noise. So if something has a 1 millivolt noise and the output of some sample is showing to be 2 millivolts, that does not mean that is the LOD. The LOD has to be the equivalent of 3 millivolts plus.
Okay. So I think there are other question, some question, one more question is there, but this might be the last one because we have short of time. So if you can quickly answer, like he's asking like Dr. Tripathi again, I think that there are multiple virus bacteria present in the test sample and basically how we can distinguish between them actually. So if you have like, I think this like he's asking in intermixing. Yeah.
Yeah, Professor Tripathi is asking very apt and very difficult questions for that matter. particular schema that we presented here does not distinguish between different types of bacteria or virus, but the optical sensors that we have created, which I'm going to talk about tomorrow in the Plasmonics Photonics Symposium, there we have ways to detect not only different types of bacteria, but also whether the bacteria are antimicrobial resistant or not.
Okay. Okay, so I think we cannot take any other. I think there are no more other questions also. So let us thanks the speaker again, and then I really
Thank you.
appreciate like your time, and then okay, okay. So we move to the next now. Yeah, thank the Dipankar Bandopadhyay from IIT Guwahati. Excuse me. Professor Dipankar Bandopadhyay, he's here.
Yes. Good morning.
Yeah. So yeah, let me just introduce yourself. So Professor Dipankar Bandopadhyay did his BTech from Calcutta University and PhD from IIT Kanpur. So currently he's professor at Chemical and head of Center of Nanotechnology as IIT Guwahati. And his research area is thin films, soft matter physics, liquid crystal, smart materials, MEMS. I think a lot of like other like multiple multidisciplinary aspects he's working. I can see the fluid dynamics and rheology and like a lot of other things. And he received several awards and uh, uh, and he has guided many PhDs and almost has like more than 110 research publications and also has 7 international and patents also. So he's talking about basically the genesis of a dream, like summarize I think a general topic, healthcare technologies for billions. So that is the title of his talk. So I request Professor Dipankar Bandyopadhyay to present his lecture, invited lecture, and the time is actually 25 minutes, and 5 minutes will be for discussions. Okay, Professor Bandyopadhyay, yeah.
Thank you, Professor Singh, for the nice introduction. Am I audible?
Yes, you are audible. Yes.
And my slides are also visible. Am I correct?
Yes, yeah. Slides are.
Yeah. So I first thank Professor Mishra and Professor Khare for inviting me in this forum and to share my viewpoints as well as the technological innovations that are taking place at IIT Guwahati. Okay, so see, I was just thinking that this is an electronics conference. So what should I do with the healthcare innovations? But then finally, I realized that it is since the participation will be very generic in nature and it will have a kind of international fragrance associated with that. So I just thought that whatever we are doing at IIT Guwahati for last 5-6 years, I just do a kind of very brief and concise overview of the thing. So let us explore like what exactly I mean by this genesis of a dream for the healthcare for a billion. Okay. So the vision starts with like the sustainable development goals that has been set. Recently, perhaps all of you have seen this document, and the one of the major focus comes like the good health and well-being, and then 3 and 9 is associated with like industry, innovation, and infrastructure, whereas 3 comes with this good health and well-being. So now, as an IIT, so what we can really see that IIT is a place where we can really generate an idea, formulate it, okay, implement, do prototype development, and then product development. And sidewise, we do a lot of other activities like test and optimize, work and proof of concept, commercialize, and profit and loss cycle. And how exactly these technologies, which has a lot of multidisciplinary associated with them, say suppose high-end science, high-end maths, high-end physics, high-end chemistry, and then combining with biosciences, and then taking it to the level of electronics, chemical engineering, and different other engineering disciplines, how exactly they arrive, to the remote places of the country as well as across the globe. Okay, so this is a typical vision map that we have prepared here, that say IITA can be a hub of technological development, and it is an engineering institute working very closely with the hospitals around. Okay, now hospitals are going to cater the needs associated with the tertiary care, and then the primary care is associated with the e-health clinics, and IIT and hospitals and e-health clinics together do certain product development, and that we make use of in the smart villages. So I put a small picture of this northeastern part of the country. It's a beautiful place, very green, okay, and it has got 7 sisters associated with that. Of course, this model is a pilot scale model, and this can be extended to first to the country, at the same time globally. Now, how we execute this? Well, what is the bottom-up method, in order to really work on the bits and pieces, and then, get it to the level of the entire vision, accomplishment of the entire vision. So you may see my presentation will be glimpses of what exactly is the roadmap. So we start with the frugal innovations at IIT Guwahati. Okay, what are the frugal innovations? We are developing point-of-care testing devices. Okay, which is associated with what? It is associated with the detection of biomarker at the patient side, and this exactly intended for to cater the needs of what? Cater the needs of the local population. Okay, like it is going to take care of the detections at the level of the primary care. Like, say, suppose example is glucometer, hemoglobin meter, blood pressure testing devices, pregnancy kit. These are all already available commercial devices. So these point of care testing devices actually employ many different principles, as has been highlighted by Professor Mukherjee in the previous talk, that it can be a chemi-resistive principle, it can be an electrochemical principle, it can be a colorimetric, okay, it can be a semiconductor. Chemi-resistive means you have a material in between the electrodes, and you are looking for the change in the electrical properties like resistance, conductance, and all. Electrochemical means you are looking for the change in the capacitance of the sensor. Okay, these are typical 3 electrode systems. Then colorimetric means you are looking for a color change, and semiconductor means you are having SAW-FET type devices, and those devices where you are looking for the electronic changes. Now, say for a biological system, for a healthcare, if I summarize the whole set of
Excuse me. Yeah, I can see. Sorry, Ishvi, for interruption. I can see some background noise, I think. So if I will suggest actually, other than the speaker, can you please, all of you can please mute yourself, so that we can hear Professor.
I have asked the host. I have asked the host to do that. The host can do that for everyone except for the speaker. I think it is Professor Malhotra's background.
Yes, it is. Professor Malhotra's background noises are coming.
Professor Malhotra, can you, because I was trying to, now I think, now.
Thank you so much. Thank you so much. So if I really look at the sensors, these are all the different types of sensors. And then these sensors are used for different types of biological fluids, like, say, suppose tear, saliva, blood, sweat, urine, and say, suppose I can add another one, that is human breath. Okay, and then what we do detect different types of viruses or bacteria or markers here, in order to really detect different types of disease conditions of a human body. So overall idea is like, first, developed an array of sensors, and those sensors, you make use of, they are specific to the detection of, like, say, suppose kidney markers, cardiac markers. Okay, say, suppose different types. I'll give you some examples, which will give more clarity. And the idea is to use them at the patient side, at the level of primary care, because it has been now identified that 80% of the disease management happens at the level of primary care before And more importantly, like, if you can really manage the disease at the level of primary care, the translation of the diseases towards the secondary or tertiary care, it can be prevented for many diseases, and which is going to reduce the disease burdens in the secondary or tertiary care. So first example, I'm just, going away from what are the conventional things that are available. I like, say, suppose you have already a pregnancy kit, you already have a glucometer, right? Now, what we decided that we are going to focus on some of the diseases which are very much prevalent across the globe, and as well as in our country, as well as in the Northeast region. And then, we are going to focus on different types of markers in different types of analytes like urine, saliva, serum, breathe. And in that, we are going to really identify different types of new diseases which are really prevalent across the globe. So I'm going to really take 5 such examples. And you will see that, these are all very prevalent around us, but there is no such device commercially available till date. So one of these is pancreatitis. You may have heard, like, the death of Nargis Dutt, to Manohar Parrikar, to Steve Jobs, all had suffered from this pancreatitis. And, these are all basically it's an inflammation of the pancreas. But then, this is detected very late. Okay. And the problem with this pancreatitis is that it's a very dirty disease. But then the marker, that we have amylase, alpha amylase, which is an enzyme which generally, like, helps us in digest the carbohydrates, whereas lipase, helps us in digesting the lipids in the which we ingest. Okay. Now the ratio of amylase to lipase is a very good marker, for the detection of pancreatitis. So our first attempt was, can we really detect this pancreatitis? Can we really develop a point of care testing device? Some of the ranges are given in typical blood serum. So serum-based detection of this pancreatitis. Okay. So typically, like, it has 3 stages. Stage 1 is the acidic pancreas, and this is where, if you can really do a POCT intervention, then what happens, you can really go for lifestyle changes and you can really delay the disease. And that's where, like, you can really add to the quality of a human life. It is not only associated with the quality of life, it is also associated with the economics of the family, because this type of diseases are very, very costly in terms of their disease management. So if these diseases are delayed, then what happens, the family is a family also, apart from the patient, the family also have a better quality of life. So what we did, you understand that these are all enzymes, like, these are all biocatalysts. This is the typical range that is available in a human body. And say, suppose increase or decrease of amylase in blood. I'm taking one at a time, like, first I'll take amylase, then I'll get lipase, and then we'll look for, like, different ratios. So the increase of amylase leads to acute pancreatitis, pancreatic cancer, okay, bile duct blockage, whereas reduction means, there is a kidney disease, toxemia in pregnancy. So these are all typical diseases that are prevalent. And typical method is that, you use spectroscopy, which is a very costly and expert-driven method. Okay, and typically, generally, people avoid in doing these tests because they are very costly. So what should we do? So our idea was, as Professor Mukherjee was telling that, paper-based devices. So we thought to make a paper-based device where it's a very standard reaction that we have used, that that, if I make starch with iodine with certain experimental condition, what happens, starch makes a complex with iodine, which is called starch-iodine complex. And this perhaps we all have done during our childhood days, that, with iodine, this is basically like, iodine is there in the iodized salt. And then there is a starch source, which is there. Most of the food sources are starch. So if I mix these two, I'm going to get a blue coloration like this. Now, what happens? Amylase, okay, amylase, the scientific name of starch is amylose. So amylase, when it reacts with amylose, it breaks this amylose into different types of small sugars. Okay. Now, the moment it breaks those small sugars, what happens? Like, these iodine get liberated. So in that process, what happens? So initially, like, when you mix starch and iodine, it forms a complex. The moment you use amylase, what happens? It breaks into small sugars and iodine release. So in that process, there is a color change takes place. So this is the very simple principle. And how do we detect? We detect this way, that, there is a there is a sensor. We light it, we illuminate with an LED, okay, and then we detect the change of color in a transmission mode with LDR. We tested with both reflected and transmitted mode, but in transmitted mode we found out that the accuracy is much better. This is the typical color change that take place with different levels of amylase in serum. This is the calibration, and you can see that these are the blood serum samples. This is actually about 2 years back. Now we have done the field trials and all, and say the data is more or less very, very reliable. Now, one aspect here you can see that this is the situation when you put raw blood serum, because blood serum also has ascorbic acid, which interferes with this reaction. But if you put potassium iodide to the blood serum sample and then you do it, then you can see that there is a color change which is associated with only amylase. So this is the first example where we could really obtain detect the level of amylase, and one can really understand that this can be a very simple device like a glucometer which can detect amylase in blood. Now next we went for lipase, and that lipase is reacting with a triglyceride to break it down to, say, generally generates a fatty acids. So essentially you may see that this is nothing but a kind of pH sensor. So as I'm doing the reaction, more acid is generated, that means pH is going down. So that is a basic principle that we use for lipase detection. But we had one big problem, that most of the oils are not miscible with serum, which is a water-based solvent. So now how do I generate an analyte? So what we thought that we may really create an oil-water emulsion with one co-solvent. So what is an oil? Oil may be typically, say, suppose olive oil, any fat source, which is the triglyceride. Then we mix this with alcohol. Alcohol is the co-solvent, and then we had a water, so we could create a kind of micro emulsion. And we expected that maybe this alcohol is perhaps taking some oil out into this water phase, which is mixing with water, and then there is an interface where a lot of triglycerides are there. And in that situation, if I add the serum lipase, serum loaded with lipase, it is reacting to those triglycerides. And these enzymes are present in a very small amount in the blood. And in that process, you may see that there is an acid formation. And you can see that just by having a kind of indicator, acid-base indicator, you can really have a calibration. And we are doing field trials for this device. Now, how do we detect? Again, detection principle remains same. I mean, in terms of arrangement, it remains same, but the principle is different. Here, we have a light source, light detector, but then, as the color changes, the transmission changes. We use different types of colors. I think that slide is also there. Yeah, we optimize the color of the light based on the indicator, and then from there, we could really get the calibration. So this gives you an example, very simple example, that apart from glucometer, apart from pregnancy kit, how can you make a device, engineering device, which is associated with, say, amylase to lipase? The next example is that we went for albumin to creatinine ratio, okay, which is one of the very, very important factors for the chronic kidney disease. We went for both blood serum and urine, but I'm going to show you the example that we use for the urine, because this becomes non-invasive. So what is a creatinine detector? We add, a citric acid to, so this is the albumin detector or the protein detector. So we add citric acid to bromophenol blue. And then, if you add protein or albumin, it has a change of color. Whereas, if I add alkaline picaret, and on that, if I put creatinine, there'll also be a change of color. So you may see that this is the typical change of color associated with, this is the change of color associated with the albumin, and this is the change of color associated with the creatinine. And then you can put a calibration, and this is a mobile-based device. These are the slots you can see, and here you are getting creatinine and albumin, and these are also able to really give you. You can see that on the mobile, if you put an ICT platform, a very simple programming gives you the albumin to creatinine ratio. It's a typical first generation kit. This was about 4 years back, where we could really display. It's like a glucometer type device. After that, we did various stages of product development, starting from involving the design department, okay, involving the electronics people, designing the PCB, and so on and so forth, to come to a kind of concept which is called a magic box. So it's a kind of modular device operated with the help of the mobile phone, where mobile apps are there, okay, and this is all in a point of care platform. This commentary is actually telling you how is it to be done. Different types of tests are there.
Oh.
And then you insert the cartridge. And once you insert the cartridge, you perform the test. Okay. So this is the typical concept. I don't want to get into the detail here because that there is a limitation of time. So we are working on this magic box concept, where is a modular one. So in a single device, we are going to really integrate a lot of different types of devices. So this is the second one, and you know that lung monitoring device has become a kind of very attractive one post-COVID situation, because breathing rate, breathing frequency, lung volume, tidal volume, these are all very important parameters. So I'm just going to tell you the simple principle that we used here. We took a paper surface and we put a N-type CDS cadmium sulfide nanoparticle aggregate here. And then if you breathe here, what happens, like water condenses on the CDS nanoparticle. So essentially it changes the conductivity of the cell. Now that change of conductivity you can really correlate with the say, suppose when you breathe out, there is a change of conductivity, and then if you integrate a heater at the bottom, when you're breathing in, this heater actually takes the water out of the sensor, and in that process, what happens, like you're breathing in and breathing out, can be tracked. And those breathing in and breathing out, you can really correlate with the breathing frequency, forceful breathing, tidal volume, and all these things, they have been really tracked. And this is Dr. Karan Madan's setup in AIMS. This is the typical setup they generally use, for this sort of devices, this type of testings, and it is the device that we are proposing here. I'll give you a very small example. This is the typical device, and you may see in the next slide, this is the way people are testing in the labs, where you can see the breathing frequencies are coming. Okay, so one can really see the breathing frequency, lung volume, tidal volume, and all these things. So this is another point of care. You can understand that, if I integrate with blood saturation, if I integrate with this with this temperature, body temperature, so this may actually help you in deciding, whether to hospitalize the sample post-COVID or whether to have ventilation for this device. So these are typical plots that are generated by the setup by Dr. Madan's setup, and this is what we are generating, and we are comparing this at the level of field trials. Okay, so now since I have about 5 minutes, I'm just quickly going to finish two major problems, which are one is this cervical cancer, which is more of an epidemic across the country. Okay, and that cervical cancer detection happens by a very painful test, which is called the pap smear test. So essentially, from the cervix, you just scrape out some sample, and then you detect under microscope with some staining, what exactly is the level of detection, level of infection. Okay. Now, what Dr. Monica Sasdeep in CDRI, she was having a kind of urinal protein, which was very specific, which is the same protein that has been detected for the cervical cancer in the pap smear test. So she suggested us to get the protein. So what we did, we took the protein, we stabilized on the gold nanoparticle. Okay, and we looked for the change in the plasmonic responses. So what is that? We had a gold nanoparticle, we had an attacher, we put the antibody, and then the antigen is coming from the urine. And what we are expecting a change in the color signal. And in that process, we made the detection of positive and negative. We did, I think, 10 to 12. This is the typical, situation from TAME. One can say that, these are the typical nanoparticles in the beginning, which causes an agglomerate. And there is a change of the signal associated with that. And that change of the signal is the typical change of the color you can see, with the agglomeration. And that color change is correlated to, you can see that this delta lambda is correlated to. So one can really understand that these are all plasmonic responses of the gold nanoparticles, and you are playing with the refractive index that is around the gold nanoparticles in order to really detect this. So these are the typical samples that we did. This has been patented recently, and we are looking for the publication. So this is another example of a non-invasive detection of cervical cancer. So another one is, non-invasive detection of urinary tract infection. This is another E. coli bacteria. So what we did, in the urine, we went for an aptamer. Okay, an aptamer is very specific to this E. coli. So we attach those E. coli, and then there's a color change. You can see that gold nanoparticle is changing color. And detection principle remains to be the same. Like there is a light source, there's a light detector, and then from there, if there is an attachment, there's a color change. And from there, you are able to really tell that what is the change in the whether there is E. coli bacteria present or not. I just keep this one. So overall picture, emerging picture is that different types of body fluids. Like I have given 3 examples of serum, urine, okay, and say suppose air, breathing air. And then you are really looking for different types of diseases like kidney, eye, lung, heart, pancreas, and you're looking for different types of other disorders which are in a situation of there is a big number of populations who are having this type of diseases through frugal innovation at the level of primary care, right? So these are the typical sensors that we have fabricated over a period of time. Okay, these are the devices. We have a startup. Sahil is a student here at IIT Guwahati who is making a startup, making different types of these toy models of the devices. The idea is that train health workers at IIT Guwahati itself. Okay, who is going to take these devices alongside the existing pressure monitoring device, glucometer, or pregnancy kits to the ground level, and then they perform this test. So we are training this rural population, for these different types of devices. Dr. Shah is helping us. He has got a lot of health clinics in West Bengal. At the same time, he's planning to establish in Assam. Okay, they perform the test based on this software called electronic health data collection software. Okay, so through this, they measure body temperature, they measure glucose, they measure different types of other parameters that are already measurable. The devices are available. So we are planning to integrate our device with them in order to really generate health data. So what is the method? So through mobile-based detection. Okay, and this mobile-based detection where we are really planning to integrate the facilities of the data collection, AI facilities, machine learning facilities, IoT facilities. And what is the overall picture? Overall picture looks a little bit complex like this, that this is the level of the human where we are detecting. Okay, and these are the services that is provided by the tertiary care or the health clinics. But then in IIT, we are trying to put a kind of server where these health data are collected, data analysis is done, and then from there we are really able to predict in which place what are the different types of diseases that are prevalent. So these are the typical funding agencies where I have received support. Of course, you have seen that in all the slides I have mentioned about the students who are involved associated with these works. I just wanted to finish with this picture of upcoming Center for Nanotechnology building as a head. I just want to wish that all of you visit sometime. Okay, so this building is nearly complete. Maybe in early next year you will be able to see a lot of glimpses of this building that is coming on the open front. Thank you so much for your attention.
Yeah, okay. Thanks, Professor Dipankar, for such a wonderful or also well timed time also. So yeah, so now the dice is open for any questions and queries. If from the participants, if you have any, or you can type on the chat box also, so I can read out. Yeah, so till the we received some questions from the participants. So any query? Let me just check maybe. Yeah, so if you have any query, you can just participants. If you have any query, you can type on the chat box, or you can directly or some who are joining, they can directly ask also. So I have one like small things to just to ask maybe, and we can wait for person to ask the question. So regarding your like that portable breath sensor, you have shown that device probably. So have you like how many cycles it can take, or like, or you have to like what is like the reusability of these kind of devices maybe? How many cycles they can?
Yes, for a given patient, it's a use and throw sensor. But for a given patient, you don't reuse it because these are all paper-based, very low-cost sensors. So, but for a given situation, you can do as many as you like. So it is not absolutely an issue because you have a heater at the bottom, you have a paper at the top, CDS is at the top. So whatever water is condensing, you are evaporating out during the breathing cycle, and during the breathe out cycle, what are you doing? You are forcing the water, and that is condensing. Okay. So you can do as many times as possible during the breathing for a single patient, but it is not advisable for breath-related things because a lot of virus and bacteria are coming. So if that is reused for the other person, so it's a use and throw low-cost sensor.
Okay. So like, have you checked like with your like how much normally is the cost just for?
Yes, these are all we are planning. Like right now the cost is a little bit higher because we are doing by cutting and coating in a very laboratory scale manner. So it is coming about 40 to 50 rupees right now with all the logistics, including manpower and all. But if you go for a large scale production with screen printed paper and all, this will come to be about 5 to 10 rupees maximum.
Oh, okay.
Typically, one glucometer sensor, you will find it about 10 to 15 rupees. So it is like that only. It will come out to be like that only.
So this is really wonderful to learn about like this, like low cost, and really in this current scenario, probably your sensor and then your will be very useful because I think we are also moving towards the e-health program and those kind of things and portable things. So so I really thanks again for delivering such a wonderful talk. Thank you, Professor Dipankar. And now we are so now we are moving to our next invited speaker. He's like Professor Malhotra. So are you here, Professor Malhotra? Professor Malhotra, can you hear me? Professor Malhotra, can you hear?
Professor Malhotra is here, but he is muted.
Oh, Professor Malhotra, can you unmute yourself?
Yeah. I think he has unmuted him.
Yeah. So, Professor Malhotra? Yeah, I can see he's unmuted now, but I cannot hear him somehow. Professor Malhotra? Can you hear me? Professor Malhotra? Yeah, we can hear, but there is a lot of background noise. Can you hear me? Can you speak out maybe so that we can figure out whether we can listen you or not? Professor Malhotra? Currently you are unmuted, we can see, but if you can say something, then we can hear, we can figure out. Yes, looks like there is some. So again, I'm just checking. Professor Malhotra, if you can hear us, then hear me, then you can just speak out maybe, because currently from the meeting, like I can see that you are already unmuted. Yeah, I think we are facing some problem. So,
कैसे करूं मैं, मुझे समझ में नहीं आ रहा.
Professor Malhotra,
तो कैसे करें फिर? अनम्यूट
नहीं नहीं,
म्यूट करूं क्या करूं, अनम्यूट करूं?
अभी आपकी आवाज आ रही है. नाउ यू कैन, आई थिंक वी कैन हियर यू. यू कैन जस्ट maybe you can
एंटर कैसे करूं, ये समझ नहीं आ रहा.
no, you can
अच्छा,
you share your slide ना.
समझ में नहीं आ रहा मुझे.
प्रोफेसर मालहोत्रा, आपका स्क्रीन का नीचे एक शेयर बटन
ये
रहेगा.
अभी म्यूट करना है, अनम्यूट करना है?
नहीं, अनम्यूट ही रखिए. अरे म्यूट कर दिया आपने.
नहीं, आप या प्रोफेसर मल्होत्रा, आपके उसमें एक शेयर बटन, you can click that and then you can share your slides.
सेलेक्ट क्या करूं, सेलेक्ट अपनी प्रेजेंटेशन करूं?
हाँ, शेयर में आप you just select your presentation, you share your presentation.
ये तो नहीं आ रहा मेरे पास. हाँ, यस, माय प्रेजेंटेशन इज ओपन.
नहीं, आपको वेबएक्स का जो प्लेटफॉर्म है ना, उसका
आया?
नीचे आपको म्यूट स्टार्ट वीडियो, उसका
आया क्या?
शेयर मिलेगा. दबाइए.
नीचे बॉटम में देखिए प्रोफेसर मल्होत्रा, नीचे बॉटम में.
स्टार्ट वीडियो नहीं करा.
नहीं,
अब आ गया.
हाँ हाँ, वीडियो तो आ
अब
गया,
क्या
बट
करूं?
वीडियो के पास में देखिए साइड में एक शेयर का
शेयर विद
ऑप्शन आ रहा है
स्क्रीन.
ना.
शेयर कर स्क्रीन. हाँ, आ गया, स्क्रीन आ गया.
हाँ, शेयर अभी
हाँ
तो अब इसको वो कर दूं.
हाँ.
स्क्रीन कर सकते हैं.
ओके.
Okay, so yeah,
अभी
so
आप दिखाई दे रहा है अभी?
yeah, we can see it.
And you can hear me also?
Yes, we can hear you.
Okay, thank you.
Okay, so let me just
Good afternoon. My name is Bansi Malhotra. At the outset, let me thank Professor Mishra and Professor Khare for giving me the opportunity to be with you this afternoon. And I am going to talk to you on some of the nanostructure metal oxides based biosensors that can be used for oral cancer detection. And this is the sequence that I'm going to follow. You all know about what nanomaterial is, but just to be on the sure side, I will display just one slide. And then of course, biosensors, all of you are experts, maybe one slide for biosensors. And of course, eventually I'll go to what cancer is and how can we use the various nanomaterials like zirconia argeo, serine, functionalized zirconia, and several others. So depending on the time, I will try to describe some of the results that we have obtained at Delhi Technological University, the Department of Biotechnology. So everybody knows nanomaterials now. About 15-20 years ago, nobody will worry nanomaterial, but worried. All are concerned as to why did I not talk and read nanomaterials as such. So nanomaterials came into existence or about 50 years ago. I was told that there is plenty of room at the bottom. And it was Finman who coined this, and since then there have been many Nobel Prizes, starting with carbon nanotubes, graphene, carbon and buckyballs, etc. And then, of course, the quantum nanostructure metal oxides, and in which we have been working to fabricate biosensors, are being widely used. And of course, you can have conductive polymeric nanomaterials as well as such. So these nanomaterials have a very varied variety of applications and for biomedical applications and particularly in biosensors. But you can use this for nanomaterials for drug delivery, tissue engineering, and also, of course, and also biosensing. A biosensor is an analytical device that recognizes and converts a biological signal into a measurable signal, and you don't require any reagent. Reagents are already immobilized, and some of the characteristics that a biosensor should have is that it should be highly specific. It has an emulsion matrix to create the conditions for the shelf life or the long life of the biosensing or biological molecules that act as biorecognition elements. And transducers, of course, is required to convert the biological signals into measurable signal, and then, of course, the digital readout. So these are some of the characteristics like affordability, sensitivity, specificity. It should be user friendly, should be cheap, it should be deliverable, and it should be provide rapid information, and of course, should not verify it falls down on the floor. We should be able to reuse it. So there are lots of things I can continue to. And the advantage of biosensors, as I is that they are highly specific, they are rapid. I already described this a little while ago. And then they have non-clinical applications to find out whether the fruit that is available on the plant or on the tree is ripe enough, or is good enough to be plugged in. And similarly, the biosensors applications in nanometry in clinical laboratories, you can use it either in vivo or vitro. So in vivo is applications of the materials are still being researched, and they are not yet at the advanced. They are not yet caught the market, or even at the laboratory. They are at the laboratory scale. So in vitro applications are the ones which we are going to talk about. And then we developed one glucose biosensors, and which is available in the market. I'm not going to talk about it, but what I used to talk is cancer. Cancer is abnormal and uncontrolled cell growth that occurs due to accumulation of specific genetic and epigenetic defects. And essentially, it is an unregulated cell growth as such. And in other words, in the cancer, the apoptosis is hampered, and then the tumor cells become resistant to apoptosis, and then eventually affect the defense mechanisms in the system. So we are worried. We want to find out whether the cancer can be a variety of various types. You can have lung cancer, which is most common in men, and breast cancer, which is most common in women. And you can have blood cancer, you can have cervical, and the list is endless actually. So what we are going to talk is oral cancer as such. So oral cancer is uncontrollable malignant growth of cells in the system, in a body or in a living system. And then the risk factors include smoking, tobacco, high alcohol oxidants, poor nutrition, poor hygienic conditions, and it occurs more often in men than in women. I already described it. So there are lots of people who about more than 59% of the people in less developed countries are suffering from it, and again, rest of 41% are in the developed countries as such. So the present diagnosis is done by imaging, computer tomography, magnetic resonance imaging, vital staining, cytography, or even biopsy. Actually, is the gold test. Is the only confirmatory test which is available till date for diagnosis of cancer as well. So the disadvantage of these techniques are that they are highly invasive. The sample collection has to be done, and should you have a highly trained persons require time taken in obtaining results. It takes about 1 to 15 days, and the cost of the operation to treat the cancer patient is also very high. So most of the condition, and they cannot be utilized in remote areas. So what to do about it? Newer techniques are being evolved, and you can use fluorescence, you can use Raman spectroscopy, you can use optical technique, and of course, biomarker profile is a very important method to detect cancer in saliva as such. So there is a shift towards the evolution of non-invasive diagnosis of a disease, and that too particularly of non-cancerous disease. So biomarker can be DNA, can be protein, can be glucoprotein, or it can be a peptide nucleic acid or microRNA. And these are some of the biomarkers that have been researched with or are being researched. So the test specimen can be sweat, saliva, or even saliva is the most, or even ear wax or nose discharge, and urine as well can also be utilized. So questions that that a cancer biomarker answers is, do I have a chance to develop cancer? What type of cancer is it? Is it optimal? And if it can I predict a cancer, or can I the cancer? So these are some of the problems that the patient will ask. And there are various biomarkers that have been evolved for oral cancer detection. And you can have interleukin 1, interleukin 2, interleukin 6, interleukin 8, and interleukin 1, and 1 beta as well. So CIFRA cytokeratin fragment is the one which is available, which has been found to be sensitive to the existence of oral cancer. So up to 3.8, its concentration in CIFRA concentration in saliva can vary from 3.8 nanograms to 18 nanograms per milliliter in a healthy patient. Anything below or above this will indicate the presence of oral cancer. So advantage of saliva, using saliva, many it is non-invasive. Today also there was some report in the newspapers that you can use even saliva non-invasive saliva to detect even COVID-19. So there is a lot of scope towards towards diagnosing the presence of oral cancer in or any disease rather in using the saliva as such. So one such experiment that we tried to do was to fabricate a nanostructured zirconia-based biosensor for non-invasive oral care. And this paper was published in Science in 2015, and it has a high impact factor. So we want to use zirconia is highly compatible. It has a better film forming property, and it can use its electrochemical and surface charge properties. And then of course it has and thermal properties. So we just zirconia oxide and treated it with sodium hydroxide and started at 300 revolutions per minute at 60 degrees and for 48 hours, and we ended up having zirconium hydroxide. And then this zirconium hydroxide thus obtained was put into a hydrothermal pressure at 170 degrees for 15 hours, and zirconium oxide was found, and it was eventually calcined at 400 degrees centigrade for 3 hours, and we ended up having zirconia. So this is the schematic. We took IPO and we put hydrolyzed it. We electrochemically deposited zirconia that I just described onto by electrophoretic technique, and the voltage used was around 11 volts, and it was deposited for around 20 seconds or so. And then after we had done it, we linked the EDC NHS system onto this particular electrode to tag so that it provides sufficient groups to tag the APTS as such. So then we use Bowman serum albumin to passivate the unused sites, and then the CIFRA antibodies were put onto it, and then the test specimen contains CIFRA already. So as a result of the reaction, we can generate a potential or a current. Essentially, we looked at the current, and we looked at the X-ray diffraction investigations, and we found that the JCPD shows the comparison shows that zirconia is in monoclinic phase, and we found out using the transmission vector microscopy and the high resolution transmission electroscopy that the size of the zirconia is around 50 nanometer or so. So, and it has sufficient roughness so that the large amount of antibodies can be loaded onto it. So we did the atomic force microscopy and FTR investigations to find out about there is a linkage between the electrode and the antibodies as well. So we and the FTR spectra at 1629 centimeter inverse or so. And then the photoelectron spectroscopy results measurements were also done, and we found a peak at 400.3 that correspond to the covalent bond formation between NH2 and APTS as such. So we did the electrode measurements to find out of with these different electrodes as such, and we found that the incubation time of this particular system is about 20 minutes or so. And then, of course, we made a comparison between ITO and ITO treated zirconia and APTS treated and BSA treated. So we found sufficient changes to indicate that this will work. So sensitivity of this electrode obtained using differential pulse voltammeter technique was about 2.2 milliamperes milliliter per nanograms, and the detection range is around 2 to 60 nanograms per milliliter. And the detection limit was sufficiently low, around 0.08, but not large enough to be used as commercially as well. So we looked at the electrical samples and also the effect of the various interference like glucose, urea, carcinoma, embryonic antigen, and blood itself, as you know, contains hundreds of molecules which can interfere with the results obtained. So the limitation is that it doesn't cover the whole range such. So and the response time is 20 minutes, which is not bad. If there's a dead disease, you can wait for even half an hour to get the confirmatory results. So we wanted to find out if I can use another electrode, which you get, or a composite, which of course zirconia and reduced graphene oxide. Reduced graphene oxide, you all know, it has a large surface area. It has a good conductivity, and it is biocompatible as well. So it has excellent charge transfer properties. These are some of the comparison that was made and how the material was functional. I'm not going to read it out, and as I understand that this PPT is going to be on the web for some time, for about a week or so, so you can have a look at it, or otherwise you can go to the Google and find out about the details of the synthesis of the zirconia and RGO, and also functionalization of zirconia RGO. So this is it. At the XRD, and we trying to find out that the results obtained indicate that it is again in the monoclonal phase, and the size of the peaks that we obtain at about 24.2 degree and 43 will indicate the presence of reduced graphene oxide as such. FTR, as in the also atomic force microscopy investigations, and then we found that as we load the system with different groups with BSA, or the roughness of the surface increases, which was helpful for us for the loading of the larger amount of antibodies as well. So as in the earlier case, we did these measurements to find out as to how the incubation time is, and we found that the incubation time was sufficiently close to 16, not sufficiently, about 16 minutes, so which is a good results. But it was from 2 to 20 nanograms per deciliter, and the sensitivity was also less, around 0.756 micron per year. So we and of course looked at the effect of the various interference, and we found that the effect of the interference to the DPV the current obtained was minimal as such, or within the reasonable range. So this is the limitation. So we couldn't detect the range is physiological range is 0 to 3.8 nanograms per milliliter, and we look at differences. Antibodies as such. So these are some of the differences as I just described. So serine has both OH and H2 groups, which will help us. So this is the transparency was already shown, and we fabricated the electrode, and we were at 50 volts for about 35 seconds or so. It was electrophoretic deposition. Most of all the measurements that I described, they were done by the deposition was done by electrophoretic technique. So it is a mixed phase, and then we found out that the it is a monoclonic. It is in monoclonic phase, and then we looked at also the biocompatible investigation with using HeLa HEK293 cell line, and 95% of the cells remain didn't die. So which means it is a good system uh, for uh, for a robot or for a sensor to be put into a live system as such. So cytotoxicity was very low, but the sensitivity was again not very sufficient, was not as good as the zirconia-based biosensors. So the detection limit was of course reduced, and the linear detection range was from 0.01 to 29 nanograms per deciliter. And we also looked at the real levels, which indicated the presence of like glucose, cholesterol, urea, or even lactate didn't affect the response of the results obtained. So limitation was the sensitivity. Didn't stop here. I'll describe some results with the Hafnia. Hafnia has a material, hafnium or hafnium oxide as a material which has a high dielectric constant of about 23 as compared to urea, which is sufficiently low. That I will describe in a few minutes. So Hafnia was prepared as the schematic of Hafnia that was used to, because the time is very less, so I'm skipping, I'm going to his pages very quickly rather. So calcination was done at 400 degrees for about 3 hours, and Hafnia was obtained. And then X-ray diffraction and transmission electron microscopy investigations were done to tell out that the average particle size of Hafnia was 1 nanometer or so. And TM investigations were also to find out about the roughness of the the atomic force microscopy and TM investigation were done to investigate the morphology of the system. And the roughness, average thickness of the system material of this probe was around 4.7 nanometers, which increased to 7.1 nanometer upon emulation of the CIFRA antibodies also. And BSA was utilized to block the non-specific sites of the system. So, and then the X-ray photoelectric also done, and we found that the peak existing at 5 to 130 electrovolts is assigned to Hafnia, and then of course the peak found at 399 electrons was attributed to the nitrogen-free amino APTS, which is a linker. So similarly, we looked at the FTI investigations with and without antibodies, and we were convinced that the linkage of antibodies has been APTS linked Hafnia put onto ITO exists as such. So we looked at the electrochemical response, and the linearity of this particular system was 2 to 18 nanograms per milliliter, and the sensitivity was around 9.28, which is also fairly low as compared to the zirconia system that I described in the few minutes ago. So linearity is low. Detection limit is also not very very good. So we left on to found out if the agglomeration has something to do. Agglomeration of Hafnia has anything to do with it. So we found out that if we correct RGO with Hafnia or vice versa, there is a possibility that the agglomeration can perhaps be improved as well. So this was some of the reasons, and as in the earlier case, some of you who are interested in trying to find out the protocol, they can have a look at presentation or they just describe. So this is it. This is the schematic of this particular system, which was used to fabricate the BSA, anti-CIFRA, APTS, Kenya, RGO, ITO. And then we found that the particle size was sufficiently reduced to 10 nanometers, and it was in the monoclonic phase as such. So this results is around, sensitivity is around again 18.24, far less than to zirconia, and the detection range is around 0 to 30 nanograms per milliliter, and the detection limit is reduced, but we want still lower than that. And the results were compared with the clinical samples, and we found is sufficient reasonable agreement with the system. But the limitation is the bit size. So this is a new result which was published last year on using deuteria. The reason we use deuteria was that this is a low dielectric constant material. We have worked on dielectric, low dielectric, high dielectric, and also we change the linkers to by serine compared to widely used IPTS system. And we wanted to find out if deuteria or the low dielectric constant material will have any decisive effect onto the response characteristics of the particular electrode for oral cancer detection, for oral cancer. So these SCM pictures were taken on the field emission, and we found, and we also looked at the cell viability, which was around 95% up to 50 microgram per milliliter concentration of deuteria, after which the cell viability was found to be decreased as such. And we looked at the cyclic voltammetry investigations, and results were reasonable agreement. We looked at the response of this particular electrode, and we found that the detection limit is 0.33 nanograms. We want lower detection limit as such. So shelf life was not very good. So when we compare these results with this particular system, the response time is also around 30 minutes, so which is decreased, so which has deteriorated as compared to other systems. New result which is just published, and with the mass material research corporation, we took up the nanodot zirconia for construction of the non-invasive oral cancer biosensor. And we found that this particular system has had the interesting results. And the results were, of course, compared with clinical samples, and the detection range was obtained from 0.5 to 50 nanograms per deciliter, and the detection limit was 0.4. So we are not yet reached to where we want to reach, and detection limit has to be improved towards this for the system. And the work is in progress at the National Nanobioelectronics Laboratory of Delhi Technological University, wherein we are trying to use guar gum hydrogel zirconia for biosensing platform. And last night we communicated the paper on which based on deuteria doped zirconia reduced graphene oxide, which shows excellent results as such. So maybe I'll have a chance to present the results of this finding a little later. And in conclusions, what I wish to mention is that the coagulation of nanomaterials effort should be made to decorate nanomaterials like reduced graphene oxide and carbon nanotubes. And then the effort should also be made to obtain more biocompatible systems, and alternate cancer linkers can be used, and it should be interesting to utilize the non-invasive biological fluids such as urine, sweat, tear, ear, and nose wax. As I mentioned in the beginning, this is highly required. And then, as I mentioned in the beginning, first slide, that the effort should also be made to utilize some of these platforms for mobilizing the antibodies for COVID-19 detection as such. There is a good opportunity for non-invasive for construction and report of the biosensors. So the work that I have described has been in fact was initiated by Dr. Sovin Kumar, who is presently a inspired faculty fellow at Delhi Department of Chemistry, Delhi University. And so what I have described here is because of these people. I am just an actor who tried to describe some of the results that I think Shine Augustine is going to talk after me for her results obtained for breast cancer detection on in the laboratory for her PhD program. So some more people, thank you very much for both. Thank you so much. All the life is an experiment, and the experiments we do, we perhaps better it will be. Thank you so much for your time, and if there are any questions, I will be happy to answer. And thank you.
Okay.
Can you hear?
Thank you.
Hello.
Yeah, we can hear you. Thank you, Professor Malhotra, for. Yeah, we can hear you, Professor Malhotra.
Hello.
I think we can hear you. So thanks for your talk. And then now we just request all the if you have any query, any other participants, ask some question. So participant may ask some questions if you have. So if you want to ask any questions to Professor Malhotra, then it's open now. Yep. Professor Malhotra, can you hear me? Yeah. Can you hear me, Professor Malhotra? Yeah, I think.
अब आ रही है. अच्छा फिर दोबारा करूं? अच्छा, I just wanted to find out if anybody has any questions to ask. Okay, thank you so much. Presentation तो हो गई कि नहीं हुई? Okay, thank you so much. क्योंकि यहाँ से पता नहीं चलता.
Okay, if I think there is some problem in communication probably. So so we thank Professor Malhotra for such a nice talk, and I hope like his useful for that COVID-19 which he is proposing, which is one of the current like demand maybe. So let us move to the our next speaker. So yeah, Professor Malhotra.
Hello.
Yes, maybe let me see if we can just. Yeah, Professor Malhotra. So we can just. Okay, so let us move to the next speaker. I think there is.
So I can. Okay, thank you.
So let us move to the other speaker. Yeah, Miss Shine. From she's from DTU, and her title is. Yeah, her title is Highly Sensitive Transition Metal Oxide Nano Hybrid Based Conductive Platform for Cancer Detection. So Shine, you have basically 12 minutes maybe for presentation, and 3 minutes will be for 3 minutes will be for discussion.
Sure, sir.
Your questions. Okay, you can start now.
Sure, sir. Okay.
All yeah, 1 minute. All other participants or maybe speakers might mute their microphone. Okay. You can start.
I'm just sharing my presentation. Yes.
Yeah, I think it is going to
Hello?
be. Yeah, it is going to be visible. I think it's something is there
Okay,
now.
okay, sure.
But right now we cannot see your presentation. Like it's showing weaving your Shine's application something, but maybe yeah. I think yeah, it's coming.
Okay. Very good afternoon to all the delegates present at IEEE Icee. I'm today presenting on my title. Just a second. Sensitive transition metal oxide nano hybrid based conductor.
Shine, we cannot see your slide.
Yes, sir. Okay.
We cannot see your slides.
Just a second.
Yes. Now we can see your slide. That's fine.
Okay,
yeah,
sir.
Yeah, go ahead.
Just a second, sir.
Make full screen and then go ahead, maybe. You can make it full screen.
Is it fine now?
Yeah, now it is fine.
Okay.
Perfectly.
So this program at Delhi Technological University under the supervision of Professor Malhotra and Professor Pragati Kumar. So I'll just start with the whole contents of my presentation would be focusing a brief about cancer, followed by breast cancer, the conventional techniques and challenges, and the fabrication of immunosensors, the results which I have obtained while during the experiments, followed by conclusions. I'll just give a brief about cancer. Cancer, as we are all aware, it's an abnormal cell growth having potential to invade or spread to other parts of the body. Generally, cancer, as reported by WHO in 2018, it was estimated around 9.6 million deaths caused due to cancer only, among which the major types of cancers are lung, prostate, breast, and colorectal. Among these different types of cancer, that breast cancer stands at the fourth most death-causing cancer. The report by National Health Report by India in 2018, it was published in 2019, as you can see. It was observed that the number of cancer cases are gradually increasing every year as compared to 2017 and 2018. And definitely, this is an alarming number that we need to work on something where we can diagnose cancer, if not at a very early stage, at least at the primary stage, where we can handle cases rather than getting it diagnosed at very advanced stages. So, switching to the breast cancer specifically, the data says each year about 1.6 million new cases are diagnosed worldwide, over which 5 lakh women die of this disease. And as reported by ICMR India, every 2 women newly diagnosed with breast cancer, one is dying of it. So seeing this number, which is very alarming, that among every 2 women newly diagnosed, there is 50% chance of survival. So the current conventional before that, I'll just tell about the cause and risk. The main cause at the current causes are obesity, lack of physical exercise. Definitely, it's because more of our lifestyle, alcohol consumption, ionizing radiation, having children late or not at all, older age, family history, and lifestyle. Definitely, lifestyle plays a major role where we are tending more prone to lack of physical exercise leading to obesity, which are I'll just summarize it as interconnected. So what are the specific symptoms? Specific symptoms for specifically in the initial stages, which is not at all visible, whereas what we can find in case of breast cancer is the presence of lump. If there is a presence of lump which is painful on the breast, on either side of the breast, under the breast, or under the arm or near the collarbone, and if the lump is painful, if there is any bloody breast discharge, especially from a single or both of the breasts, then definitely these kind of symptoms should be noticed and should be taken care. As we can see on the left side, the estimated number of the incident cases worldwide in both the sexes, where breast cancer is equivalent to the lung cancer for the number of cases diagnosed. So these high risk factor alters the expression of genes in the breast, as I just told, due to which an undifferentiated and uncontrolled growth occurs in women. The conventional techniques which are being currently utilized are: one is biopsy, mammography, immunohistochemistry, FISH. Mammography is another non-invasive technique. MRI is also one of the technique, but biopsy is one of the authentic process, or let's say gold standard technique, where they collect the samples from the site and then they go for culturing. Generally, even now, it takes 7 to 10 days for a biopsy results to be produced. And the disadvantage of using these are that of X-rays used. With the use of X-ray, it shows adverse effect on the body cells, as well as discordance between the diagnosis by IHC and FISH, where they require a personal expertise view for finally coming to a conclusion. To overcome or to intervene between these gap of the current conventional techniques, we need an authentic method that can be cost effective, also can diagnose or differentiate quantitatively the stages of cancer, and it is rapid enough, or at least it should show as an indication, yes, that the results are alarming. So biosensors, basic biosensor, because we have been studying in the whole session. Specifically, if I'll go with in breast cancer, the biomarker which I'm focusing on is human epidermal growth factor receptor 2. It is a biomarker that is secreted in normal cells as well. It is a transmembrane glycoprotein which has three parts: a cytoplasmic domain, a transmembrane, and an extracellular domain. Specifically, this extracellular domain is known to cleave from the tumor site, and it is circulating in the blood. So this extracellular domain is cleaved from the surface of the breast cancer cell and is released into the serum. This serum, this ECD HER2 can be detected by biosensor. It is a growth stimulating protein. Normal cells express a small amount on their plasma membranes, but in cases of cancer, it multiplies almost 100 times. This particular HER2 protein sends messages from the cell to the growth factor outside the cell. We look upon this HER2 is secreted in serum. It is proteinaceous in nature. It is secreted in an amount. If we go for the normal range of HER2 in humans, the cutoff value is around 0 to 15 nanogram per ml. But if it goes up to say 75 nanogram per ml, then definitely it as the concentration increases, the different stages of breast cancer also can be diagnosed. So HER2 is considered as a useful serological tumor marker for clinical management of breast cancer. Therefore, detection of HER2 in serum may be an interesting alternative for clinical diagnosis. So in our work, we have used HER2 monoclonal antibodies for fabricating the biosensor. The nanomaterial which I will be focusing, the transition metal oxide which I have selected is nanostructured molybdenum trioxide. Molybdenum trioxide, basically molybdenum belongs to the D block elements and it belongs to a layered structure, transition metal oxide family having layered structure. The certain properties which I would like to highlight for MOO3 is it has different oxidation state which helps in further immobilizing and biomolecules. It is biocompatible in nature. We have also conducted studies for biocompatibility for this specific material. It has a surface area, a band gap which can be tuned if we want to increase its conductivity. It has high surface to volume ratio. It is non-toxic and excellent electrical and electrochemical properties, which has drawn attention for this particular type of material to be synthesized in the form of nano. As during my work, I came to know that MO3 individual for the fabrication of biosensors suffers from poor electrical conductivity. So, in order to enhance its more stability and electrical conductivity, I introduced a carbon substrate, that is MWCNT, which is a very known conductive substrate, and specifically amine functionalized MWCNT. Amine functionalized MWCNT mainly has certain properties like it has ease of functionality, large surface to volume ratio. Presence of amine groups aids in immobilization of biomolecules. So I don't have to functionalize MO3 to introduce any biomolecule onto its surface. Enhanced electrochemical reactivity and definitely promotes absorption of molecule. So in situ synthesis of molybdenum trioxide with MWCNT using one-step hydrothermal process results in enhanced conductivity where MWCNT provides a large number of entry sites for biomolecules and molybdenum trioxide attaches to its surface in order to provide a synergistic effect to this composite. This is just a schematic view which I have proposed, where I've taken indium tin oxide conductive substrate and deposited the synthesized nanomaterial onto that using electrophoretic deposition. Further immobilized monoclonal anti-HER2 antibodies, which is further functionalized with BSA has been used for blocking the non-specific sites, and then HER2 antigen has been introduced for further interaction. The confirmation of the composite synthesis was performed using XRD studies, and it was confirmed that the MO3 and MO3 nano composite with MWCNT definitely showed peaks which were in correlation with the MO3 nanomaterial, and the broad peak of 040 overlaps with the characteristic peak of amine functionalized MWCNT. and the XRD thus confirms the synthesis of MO3. Further, we also opted for SEM studies in order to confirm what is the size and the shape. So, for pristine MO3, it was found the nanorod synthesized for around 100 nanometer. When image B shows that the composite itself, we can see that in the CNT has completely wrapped around MO3 nanorods, forming an forest type or interwoven structure. AFM studies were further conducted pre and post immobilization of antibody, or I'll say specifically biomolecule. And I can see that before immobilization on the image C, the rough surface has been shifted to a globular morphology or a smoother surface, further confirming or supporting that antibody has been macromolecular structure has been immobilized onto this particular deposited material. We have further confirmed this immobilization of antibody with FTIR studies, and we can see that the amide bond formation occurring at the peak at 1700 and 1382 confirms the presence of amide bond. To observe the presence of NH2 and WCNT in this composite, we have individually studied each of the material, and we came to a conclusion that using EIS, impedance spectroscopic data, we come to know that after introducing NH2 and WCNT with MO3, the current characteristic enhanced almost 40 times with respect to just bare MO3. So the hypothesis like introducing or enhancing the electrical conductivity definitely was overcome after introducing MWCNT. Further, I have also performed electrode study at each step of fabrication, and we can see that the highest, in the hybrid state, or I'll say the nanocomposite of MO3, NH2, MWCNT, ITO, the maximum current characteristic was obtained for MO3, whereas after introducing antibody, the resistance increased, we can see in the EIS study, and after introducing BSA, the resistance increased even more. This increase in resistance definitely is attributed to the nature of biomarkers. Further, we have also studied the electrochemical scan rate study in order to find out whether it is a diffusion control process without introducing biomolecule and post immobilization. And it was confirmed that in both the cases, the electrode showed controlled diffusion controlled state. We also calculated the diffusion coefficient in the presence and absence of antibody, and it was found that with the presence of antibody, the diffusion coefficient decreased. pH study was further confirmed in order to further. It was found that at pH 7 or 7.5, the highest, there was a marginal difference. So throughout the experiment, we have used pH 7 for our studies, where it has showed the maximum current characteristic. Further, this electrode was further incubated to in order to study the interaction time with antibody and antigen. It was found that around 15 or 20 minutes is the approximate time for the antigen to interact with the antibody and produce a specific result. We have performed the electrochemical response study using differential pulse voltammetry, and it was found that this particular sensor is showed linearity against 10 to the power minus 6 nanogram per ml to 10 to the power 3 nanogram per ml, which is definitely a very wide range with a sensitivity of 26 microampere per ml and a detection limit as low as 10 to the power minus 6. Further, this particular electrode, we also studied the control data in the absence of antibody, and we found out that in the absence of antibody, there was no interaction shown with the antigen and the electrode itself. Further, we also carried out interference study in the presence of different potential interference like ET1, that is colorectal cancer marker, CTNI, cardiac troponin, CEA, general cancer marker, and CIFRA21, as we discussed, oral cancer. And it showed that this particular sensor is definitely selective to HER2 antigen. We subjected this particular biosensor to real sample studies. The real samples were obtained from Rajiv Gandhi Cancer Institute, and we obtained 5 different samples, and these samples were subjected after dilution 20 times, subjected to this particular electrode, and the results obtained were for all the 4 samples, the relative standard deviation was found to be less than 5%. Further, reproducibility studies were also performed, and reproducibility studies showed that the percentage change, that relative standard deviation, was found to be 2.5% among 5. I've just shown the data for 5 electrodes. Electrode was found to be 5 weeks, after which the current started deteriorating drastically. Existing sensor using an optical sensor, field effect transistors, recently published, and the work which I have already performed. This particular sensor showed the best figure of merits, including the broad linear detection range, better LOD, and better sensitivity, with a response time of 18 minutes. So in conclusion, I would like to state that using biocompatible molybdenum trioxide with a carbon substrate like enhanced its diffusion, better heterogeneous electron transfer. It has provided high surface coverage for loading of antibodies, and with a remarkable sensitivity and a range. The further which I would like to suggest is if we could utilize or perform the similar experiment on to a flexible substrate as suggested by Professor Soumya in his previous presentation, that it would be a better point of care diagnosis. So we are also working on transferring the similar material, transition metal oxide. We have also performed onto paper substrate, where the work is under preparation. So from here, I'll just conclude my presentation, and these are the references, and I'm open for any question and answers.
Okay. Okay. So,
Professor Singh, can I ask a question, please?
yeah, sure, please.
Yeah, Ms. Augustine, if you can
Yes, sir.
go to your just the last slide, please. Before this one, before the fun slide. No, one before that. Yeah. No. You said somewhere it is no one. Next, please. Next, please. Almost your
Previous
conclusion
to
slide,
this?
I would say. Yeah. Conclusion slide, I think.
Yes, sir.
I mean, it something. Yeah. This one. Yes. So, I mean, you have said that lower limit of detection is 10 to the power minus 6 nanograms per ml. I mean,
Yes,
I
sir.
wonder why aren't you just going and
Okay,
calling
sir.
it 1 femtogram per ml?
Yes, sir. I could also write that way as well.
Again, I mean, on what basis are you saying that? That was not very clear to me.
Okay.
That the lower limit of detection, have you looked at the control and the noise on the control?
Yes, sir. Specifically, if I talk about, like, as we already know that we have the lowest detected antigen for this particular sensor was 10 to the minus 6 nanogram, and we did conducted this study for control without the presence of antibody as well, and also the background noise was also found. So right now we are also performing this particular efforts are being made to perform this particular sensing experiment in the presence of different serum samples, so that we could achieve a better lower detection limit, because this limit was obtained using standard samples.
Ms. Augustine,
Yes, sir.
unfortunately, when you use serum, most probably your
Yes, sir.
LOD is going to go up.
Yeah, definitely, sir.
Okay, and also when you have a control,
Yes,
and you
sir.
do a lower limit of detection, what you need to do is look at the noise of the control. Let's say the noise of the control is some
Yes,
X.
sir.
Your lower limit of detection should not be less than 3x.
Oh, yes, sir. Three
Okay, the
into signal
comparable
value.
upward. So I did not see in your graphs as to, or rather, maybe I did not notice as to.
Okay.
I mean, what was your noise in the control, and how this 1 10 to the minus 6, the output of this 1 10 to the minus 6 was bigger than that 3 times that noise.
Okay, sir. I've not shown the data here, but definitely I'll just look into it.
Yeah, please do.
Point you
Because
have
this is a
raised.
very interesting work. This is a very nice work. You have presented very nicely. And,
Yes,
you
sir.
know, I would
I'll
like
just
to.
look into it.
Yeah.
Okay. Okay. Maybe, yeah. Shine, maybe. So,
Yeah.
is there any other question? Then I'll just ask one short question, maybe, because I
Yes,
have
sir.
seen your. You have shown the AFM things where you
Yes, sir.
have determined basically the roughness. So if you go to that slide, so can you just, yeah, here, yes. So what actually I noticed actually, so here
Yes,
you
sir.
are showing that in your figure C and D,
Yes, sir.
so you are comparing the average roughness there, huh?
Yes, sir.
Yeah, but actually, what I noticed actually, the scales are quite different. See,
Yeah.
when we basically check the roughness between these samples, I think I will suggest to have the same
Scale.
scanning. Otherwise, if you change the scan area, you cannot compare basically.
Okay, sir.
So
Okay,
that's
sir.
okay. Anyway, so
Sir,
it was,
okay.
yeah. So
Yeah, I'll just keep your points and suggested points in mind, and I'll just
okay,
look forward to it.
yeah.
Work on
So,
it.
okay, so it was
Professor Singh,
good.
just one comment about
Yes,
this AFM also.
yeah.
Ms. Augustine, be very careful about using this RMS roughness figure.
Yes, yes, yes,
Okay,
yes.
Yes,
it is
yes,
a
yes.
very qualitative figure
Yes,
and
sir.
very dangerous thing to use. Okay,
Yes,
I mean,
sir.
people take all sorts of conclusions on this, but if you read up on what RMS roughness is,
Yes, sir.
you soon know that actually you cannot draw much conclusion except a very qualitative
Yes,
judgment.
sir. Yes,
Yeah,
sir. Yes, sir. Yes, sir.
but anyway, go
So,
to.
okay. Thank you, sir.
Okay, okay, thanks, Professor. And also thank you, Shine, for
Yes, sir.
presentation. And we'll move to the next one.
Thank you,
So
sir.
our next, yeah, so let us thank the speaker again. And the next presentation is by Dr. Tripathi from IIT Hyderabad. So Dr. Tripathi, are you there?
Yes, sir, I'm here. If you can hear me, please.
Yeah, we can hear you. So yeah,
I'll just close it.
yeah, you can close your presentation, Shine. And then
So can I share
Dr.
the slides?
So, Dr. Tripathi, so so the title I think today he's going to present is on polyaniline nanofibers as semi-resistive transducers, and so okay, so you can start maybe sharing your slides, maybe presentation. You can start sharing.
So the screen is visible to you?
Yeah, now it is visible. You can make I think the full screen. Yeah, that's wonderful, wonderful. Now we can
Okay,
see it.
okay,
So
sir.
you
Okay. So,
so you have
so let-
again 12 minutes of
oh,
presentation and 3 minutes of discussion. Okay.
yes, sir. Yes, yes.
Yeah. Please go ahead. Yeah.
So at the onset, I thank the arrangement team and the entire team of ICEE, and I'm quite glad that Dr. Mukherjee is also here because this talk looks like an extension talk of what he spoke in the earlier lecture. So I'll be glad to know his feedback. We'll talk about polyaniline nanofibers transducers and their application into DNA sensing. Of course, DNA sensing here is just a case study. They can be also extended to different applications such as immunoassays and others, as Dr. Mukherjee has pointed out already. We'll talk about the introduction very briefly. Then I'll explain the methods and schemes, and we'll have a conclusion, future direction. So by and large, DNA sensors, as we know, they applied into fields from disease diagnosis to mutation detection to knowing food fouling, bacterial detection, and more like COVID detection also. But the basic principle that people use or we have been using is to have a sensor and a capture probe. Of course, the capture probe comes out of this concept that DNAs are very specific to each other. The base pairs are complementary to each other. We use some kind of principle to bind them to a particular sensor. Now, once we have a hybridization complex formed where the complementary target comes and binds to the probe, and we try and transduce this hybridization principle to a physical measurable And depending on the transduction principle, we can have optical sensors or electrical sensors, or mechanical sensors and whatnot. Basically, we have been seeing a lot of electrical effectiveness, but when we think of creating point of care sensors and we think of creating readouts for them, the simplest readout that comes into mind is to create a current voltage measurement with the DC voltage. That becomes very easier for us. So in that, keeping that in mind, we people across the world, and we also have started developing chemiresistive sensors where we can just have a sensing platform which measures the current response to a DC applied voltage, and of course then convert it to a register measurement. This can also be done with AC measurements also. Like Dr. Mukherjee also pointed out, we can do AC conductance measurements. We can find capacitive or like R and X components at different frequencies. But to do a simplest readout, which can be done very easily without having any frequency or oscillators on your board, you have DC measurements. Now in that thing, chemiresistive principle come into picture. Also, it is a very prominent version of it is the biofets. When you have the biofets, generally we have a source and drain, we have a conducting channel. This conducting channel can be a nanofiber, and we have the probes attached onto it, and we have the target binding. This is just a representative figure. Of course, it is not this simple. Now, these conducting nanofibers that have been used in chemical transduction, among them, polyaniline has become a very prominent figure over the years because of its inherent properties that we can oxidize it, we can reduce it, we can know the oxidation states from the color changes, we can tune the conductivity by different degrees of protonation and whatnot. Because of this possibility that polyaniline can be doped in many ways, polyaniline can be tuned to have a range of conductivities. So this has become very, very highly acceptable medium or transducer in chemical transductions. Previously also we have worked on this. I think in IEEE census last year also we published a paper on polyaniline based DNA sensing. Just to continue from that work, in this work we go for a different synthesis protocol. Now, as has been reported, the oxidative polymerization of aniline to polyaniline to the emeraldine base and emeraldine salt form, which of course is the conducting form of polyaniline, we can add a seeded synthesis method where we can add polyaniline nanofibers, or let us say CNTs as seeds. These things have, of course, helped us creating uh, much fibrous structures, which have been suggested in literature, and we have adopted that method to have polyaniline nanofibers as a seeding synthesis protocol. And of course, once you have a nanofiber ready with you, you can decide where to put it to create your chemiregisters. Of course, in chemiregisters, we mean we have to have a pair of electrodes, as simple as that, and we can drop cast polyaniline across those pair of electrodes, and we measure the current flow across it. Now, in this work, we have used a interdistributed platform, and we have used the conventional lithography technique to develop it because it was laboratory work and part of my PhD thesis. But we have also gone beyond it, where we can create different substrate choices. Like we have seen paper based substrates, we can see plastic substrates, because the material is ready with us in a powdered form or in a compact form. We can just create dispersants and drop cast it onto any substrate, which is easier for us, and that also gives us choices to have the control on cost, production cost. We can also look at developing chemiresistive platforms with PCB substrates. We have this commercial copper clads. We can just use them and etch off the unwanted copper by this shadow masking, which can be easily done by conducting or this marker pens. So in many ways, we can create this substrate. So here substrate, we have used a silicon based substrate, but on a wafer, silicon or glass based wafer, it's a SiO2 based wafer, but this substrate choice is not very binding. We can have different substrate choices. Now, once we have a substrate, how do we create a sensor assay? I'll just go through the protocol very, very quickly. Already, most of these steps are known to us. We have a chemiresistive electrode platform, which are interdistated. We drop cast the nanofibers. So these nanofibers will create conducting channel across by breezing those metal electrodes, interdistated electrodes. And we then functionalize them so that we can bind the targeted probes onto it. In this work, of course, we are talking about the probes which are specific to this dengue viral specific consensus primers. These are 28 mer single stranded probes. This is just a case study. We can use any probe for that matter. We can also use antibodies to make immunoassays. Once the probe is bound, we can create a blocking platform using any of the blocking agents. Here we have used bovine serum albumin. Now, once we have the sensor which has the probe, we can just drop in the target of different concentrations if you want to sense different concentrations, and we can incubate them so that we can create a binding assay where the target binds onto this, and then we can wash off the unbound or non-specifically adsorbed species and dry them. Here the incubation time we have used 1 hour, and we have given 37 degrees Celsius depending on literature or experimental results. Of course, the incubation time of 20 to 30 minutes can be used. Right now we are using a 20-minute incubation protocol for our work towards COVID. But for safety and for more specific binding and to avoid non-specific binding, we can use a longer incubation time because the temperature here is low. And this 37 degrees Celsius, the choice of this temperature is also critical sometimes when you're using pani-based sensors, because these polymers are very sensitive to the temperature. And sometimes we have seen in our lab and experimental details that once we apply a higher temperature to have a better degree of hybridization, let's say 50 or beyond, sometimes these fibers gets denatured and they do not, and their property is lost. The conductive property goes out, so we cannot again bring them back to their original position. So the choice of temperature here has to be very, very carefully done.
So how many bases were there for DNA?
Right now we here have a 26 base polymer or 28 base DNA single strand sequence, and
Okay.
target is also the same thing.
Okay, go ahead.
Okay, sir. Now these are the characterization details for the fibers we have synthesized. We have given because we have a seeded synthesis method, we have much fibrous structures, and these FTI results show that once you treat pani with glutaraldehyde, 2% can be used. Of course, 1% can also be used. People have also reported using 5% glutaraldehyde for different time duration. We have used 2% glutaraldehyde for a 2-hour time duration, and depending on that, we can have functionalization. Once you required functional groups, then you can bind the target probes and then go ahead with the assay. Now, what we are focusing in this work is chemiresist detection. So the IV characterization comes into picture. Now, of course, we should understand when you do IV characterization and when you say it is a chemiregister, it should not behave as a rectifying device. It should behave as a non-rectifying device. For that, the choice of electrodes also matters, where we don't create a Schottky junction between the fibers and the electrode. So we have to make sure we use gold or something that has a work function which allows us to create a ohmic junction. Now, if we see the IV characteristics of different fibers, we see that these IV curves are almost very symmetric across the origin, but they are not very linear. Now, this non-linearity is inherent to nanofiber-based devices. When we have a drop caster structure, or even you have a single fiber structure, the IV graphs are almost always not linear for so many reasons that are well known. Now, when we have such a non-linear IV characteristic in a DC voltage range, and if you want to measure the resistance, it is a very difficult choice, because you do not know whether you can apply the ohmic law or you can take a slope, because taking slope also require that at different stages of your systems, your readout can do that activity. So what we have done, that we have understood that for a very smaller range of applied voltage, which of course less than 0.5 volts or in that range, the IV graphs are almost linear. This near ohmic range or near linearity is something that stays constant even if you use a various degree of fiber concentration from 1 mg per ml to 10 mg per ml. If you go beyond it, the degree of non-linearity may shift, but they almost remain linear in this range. So we have decided to use this linear range and constrict our analysis to this linear range, so that we can treat these devices as near linear registers, and we can apply the current, we can apply the voltage, measure the resistance through that, and we can treat them as resistors. Now, why we have to choose a smaller range? Because once we take the fibers and we create different stages, once we functionalize them, once we add the probes, once we add the target, this degree of non-linearity may not remain constant because I is proportional to V to the power n here, and the n will keep on changing for different stages. So if we start using the nonlinear range, it is very difficult to draw a parallel approach or on some reference between them. So we have strictly ensure that we use a linear range so that we need not encounter this nonlinearity which keeps on changing. Now, one thing we can also think here, which is very critical to sensing applications, is inter-device variability. That when you take a fiber dispersion of, let us say, some mg per ml, and we keep dropcasting the same amount across different registers, how do you make sure that the devices have a almost constant or near constant baseline? And this inter-device variability is something that tells us that when the sensors, the starting point of your analysis doesn't remain same. Of course, one can address them by doing normalized measurements. That has been done, but we have proposed one more approach in a previous communication, that we can use a saddle-masked based approach, and we can do multi-step drop casting. Instead of dropping a large volume of the fiber dispersion in one step, you can do multiple steps of drop casting, so that you limit the number of fibers that you drop in every step. And finally, eventually, by statistical methods, by trial and error, or what to say, you keep on reducing the error when you keep on going step by step by step. So it is very important sometimes to address this issue. We have not we have not claimed that this issue has been resolved, but sometimes by using a shadow mask when we drop cast, so that limits the overall active working area across devices, and by using multi-step drop casting, somehow the fiber resistances across different devices can be brought into very close proximity. Now, once we measure the IV resistance, because it is here, it is very important to note what technology we're talking about, or what measurement principle. Of course, we have a pair of electrodes and we drop a bunch of fibers between them. This is a very simplistic approach I have shown, where we have shown only 4 fibers. These fibers are very smaller in length, some nanometers in length, and because these electrodes have a gap of microns, so it is understandable that we need a large number of fibers, multiple fibers, to bridge them. If we have nano gap electrodes, we can also bridge them with single fibers, but given the complexity of their fabrication, it is often difficult to create such electrodes with almost a very high degree of accuracy. So we have used standardized electrodes, and we have dropcasted them, and we accept that when you do that, the nature of interconnection across fibers become very complex. And once we have such a system where multiple fibers are connected, we will encounter these interfiber junctions, we'll encounter these metal and fiber junctions. Sometimes these interfiber junctions will be physical, single layer. Now they can multiple overlaps. We can create a very complex system. Conventionally, this has been modeled in many ways as a representative structure. People say we can take these 2 contact registers into picture, then we can take this basic nanofibrous model, which is not a conventional R device. It is RC kind of structure. That's why we do AC analysis for them. And each between 2 such fibers, we can have a R tunneling, or let us say this R transfer. This R transfer models the charge transfer from one fiber to one fiber. This of course represents many phenomena, many complex nanoscale quantum phenomena. Now, when you talk about the charge transfer between these fibers, we have 2 kind of things, because current will flow from the contact through the fiber up to some distance through a single fiber. Then it will go jump from one fiber to other fiber, where this RT will come into picture. This intrafiber and interfiber transport is what is responsible sometimes for this non-linear behaviors. And when you talk about this intra-fiber transport, the charge flow across a single fiber, depending on the fiber length that you achieve to create, there will be multiple intra-fiber channels. So these electrons will keep hopping across these channels, and once they reach to a particular end, they will try to jump by variable range hopping from one fiber to other, where this RT will come into picture. So all this complex phenomena will give rise to a IV characteristic, which is eventually non-linear for a broader application of voltage. But for a smaller range, when a small voltage is there, we have a very stringent range of linear behavior, and that we can use for making chemistry devices. Having accepted that, we have created the probes, the sensors. Now, once we create the sensors, some of the basic principles that we have to keep in mind is the probe density, the what kind of binding isotherms we are getting, and of course, what is temperature and time. Now, probe density, as has been suggested in literature, if you have a sensing area, you have to have a sparse probe density. You cannot go beyond 10 to the power 12 to 10 to the power 13 centimeter square kind of density. Otherwise, you'll have this crowding and other effects which will degrade the hybridization efficiency. So, keeping that in mind, we have selected 3 microliters of 1 micromolar of probe that gives us a density of around 10 to the power 12 per centimeter square, which is in agreement with the literature. Now, the temperature, sometimes 37 degree, why it is required and why we cannot do the room temperature binding, because at room temperature binding, if you go down and down, two phenomena comes into picture. One is the enhancement of non-specific binding, and one is the difference in binding rates of mutated and wild type targets. So once you want to use these DNA sensors for mutation detection, or you want to differentiate between wild type and mutant targets, you want to make sure that both of them have the same probability of binding. And to make sure that these binding isotherms, or it has to be Langmuir like, or it has to be degenerate structure, for that the temperature selection also comes into picture, which is very important. Also, when selecting temperature, one has to keep in mind that this temperature should not affect your underneath nanofibers, because they might also get denatured, and they might lose that inherent conducting properties. Because we are using 37 degrees, of course, we know that when we have a probe and target binding, we should think of the TM, or the melting points of the probes or the targets, or we have to decide a temperature based on that. So there are some techniques that has been proposed by Agilent and some other research groups, where you can tune the melting points of these probes and targets, or the probes particularly, so that you can use a low temperature for your assay. Of course, we're looking into that, but that has not been implemented in this research. Now, once you do the IV characteristic of different concentrations of the target DNA for a given probe concentration, which we have used 1 micromolar here, you will see the resistance changes, and you can use the R, or delta R by R, to make sure that whatever inter-device.
Dr. Tripathi, maybe
Yes, sir.
yeah, you just can you just finish it like little quick, because
Yes,
you
yes.
have
Next slide, sir.
yeah, okay, fine then, yeah.
You can plot them as a delta R by R versus concentration, and you can derive a calibration. Of course, we can find out the LODs from the conventional methods, or as Dr. Mukherjee has pointed out, to know the 3x kind of boundary. What we are working on this with this also, to find a calibration which is free from this calibration curves or graphs or lookup tables, to have a machine learning based calibration, where you just feed a lot of data to the machine and train it, such that when an unseen dose comes, depending on the trained behavior, we can predict means what can be the possible dose. These sensors, because DNAs are anyhow very selective or very specific to the complementary targets, we have also tested their selectivity against non-complementary targets. Which have also tested against targets with single and double mutations, and it is very easy to differentiate the non-complementary and complementary targets, and the targets with single or double mutations. Now we can conclude that in this work, what we have done the chemiresistive transduction of DNA, and through using Pani nanofibers, we have studied their characterization and current voltage behavior. But what lacks in this work sometimes, that these are also spiked buffer samples. We have not used a serum sample as of now, or the work is ongoing. In the serum sample, sometimes we get a little more baseline. Delta R by R for blank serum samples is higher than blank PBS samples. So of course that will lead to a change in the calibration and LOD. What we can also do, that we can do a device modeling, where we can model the fiber based structures, and then we can take the negative charge that is created by the probe and targets as a function, as a Gaussian function, and we can model and predict the behavior, that how a particular probe with how a particular fiber with a particular probe might respond to a particular target dose. That can also be done as a comprehensive study. And as already we know, we can use these PANI-based devices for POC or point of care application for disease diagnosis. These are some of the references that we have used here. The reference Jang and Manohar, from there we have got inspiration to create the seeded synthesis of fibers. If there are some queries and questions, I can take them.
Yeah, okay. Yeah, thank you, Dr. Tripathi, for your presentation. And now the session is open for questions or any comments if you have.
Yeah,
Yeah.
Dr. Tripathi, you mentioned that at certain temperature, the polyaniline becomes unstable or
Yes, sir.
changes characteristics. What temperatures are those?
Sir, I have tried varying temperature from 50 degree to 100 degrees, and I have seen beyond 60 with the resistance changes drastically, and that resistance change is not reversible. If you heat it up to 50 and 55, after some time it comes back to the original range. But after a certain range, it does not come back to original, and it just keeps on degrading. Let's say we start with 1 kilo ohm or something. After 60 degree, it goes up to, let's say, hundreds and 200s of kilo ohms, and it stays there.
I wonder. I wonder whether you can heat it up just to that border and eliminate non-specific DNA because the melting temperature of the non-specific DNA is going to be quite low.
Yes, sir. Yes.
So you might be able to eliminate non-specific DNA over there by just heating it up to the border where the resistance does not change.
Sir, I'm thinking sometimes to use a pulsed laser or IR kind of localized heating, so that we can only heat at specific areas, but not heating the overall substrate to a very higher degree.
Dr. Tripathi, my problem is that if you have a pulse laser and things like that, that becomes unaffordable in the
Yes, sir.
your team is cheap, inexpensive sensor. Your pulse laser is going to take it out of that domain.
Yes, sir.
So
Yes.
you might have to take care of that. The
Yes.
other thing is that in one of the graphs, the last graph where you showed the response to various concentrations,
Yes, sir.
it was like it has a very sharp rise followed by a plateau. Okay, and I wondered whether you should have presented it by expanding the curve in that very initial portion of the graph.
Sir, actually, that's a mistake. This has been done in a linear concentration scale. The concentration has to be in a log scale. If you see that delta R by R, which starts for 100 picomolar, it is more than 50%. But because the scale is in a linear range.
No, I was just talking about the representation of your data.
Yes, sir.
It would have been better if you had shown the lower part very, with a much wider range, concentrate on the lower part so that you show that how it rises with the concentration at that very low concentration.
Yes, sir. Yes, yes, yes.
Thank you.
Thank you, sir.
Hello.
Hello.
Yeah, so if there are no more questions, I think this session, I would like to, first of all, thank all the speakers for their excellent talk. And I'm also thankful to Professor Soumya Mukherjee, Professor Deepankar Bandyopadhyay, and Professor B.D. Malhotra for their excellent presentation and new ideas about the biosensor. There were 2 talks, oral presentation, that was also excellent. So I thank all the speakers. And I think that all the participants must have an excellent platform to understand new challenges in the area of biosensor and bioelectronics. I finally thank Professor J.P. Singh, who helped us in chairing this session. And this was an excellent maintaining the timing as well as the control and question and answer. Thank you very much, Professor Singh. Now we are running a little bit late, and that is why we are starting the next session. And the afternoon session is going to be chaired by Professor T.K. Bhattacharya, who is present online. Then there are going to be 4 talks in this session and 1 oral presentation. So let me give you a very brief outline about Professor T.K. Bhattacharya. Professor Bhattacharya has got PhD from Jadavpur University. He has got excellent awards like IBM Faculty Award. He has got India Innovation Program Award, Lockheed Martin Award, and a lot of research project which is right now acting as a principal investigator. He is working in the area which is MEMS microsystems, nanoelectronics, RF analog, VLSI, etc. To his credit, he has a lot of papers as well as several patents. Without taking much time, I will hand over this session to Professor T.K. Bhattacharya. Professor Bhattacharya.
Thank you, Professor Mishra, for your nice introduction. And already we are delayed by, say, 10 minutes, so for 12 minutes. So our first speaker is Professor Manoj Verma, who is a very known figure in this field. So I am just would like to introduce a small introduction of Professor Manoj. One second. Yeah. So Professor Manoj Verma is currently a faculty of Center for Nanoscience and Engineering (CENS) in Indian Institute of Science, Bangalore. And he is an exponent in the area of biosensors for more than he's carrying out the research for 15 years, particularly in development of optics-based sensing technology. Very complicated, and a lot of good publications came out from his group. A large portion of his current research involves studying molecular sensing process in living organisms to understand their robustness and noise tolerance, combining experiments and theoretical modeling. So he will speak, he is our first invited speaker of this session, and the title of his talk is Single Molecule Sensing with Solid-State Nanopores. So Professor Mon now Dias is on you. Hello. Yeah, so you can start your presentation. Hello. Hello. Yeah. So Professor Manoj Verma, yeah. Can you? Am I audible?
Professor Verma, we can hear you. You can start sharing your slide.
Yeah. Sorry, I can't hear anything.
I think there is an issue. We are not able to hear him. Professor Verma, can you hear us? Hello.
And it shows it is. So it looks is. It
I
shows
think he
it
must
is.
be trying again. He must be trying again, I guess. Let's see.
Yeah, yeah. Let's see. Yeah, bolo.
Yes, Professor Sai. We
Hello.
can't see Professor Verma.
Hello, Professor Prashant Mishra.
Yeah. Good afternoon. We are just waiting for the speaker. There is some connectivity issues, so let us see.
Oh, okay. There is a talk. Okay. Okay.
It's a talk by Professor Manoj Verma. We are just waiting for him. Professor
Okay.
Verma,
After
can you
that.
connect?
Okay.
Hello? Hello? Professor Bhattacharya?
Hello.
Professor
Yeah.
Bhattacharya?
Yes, yes,
Yeah.
yes.
Yeah, so there has been a message from Professor Verma. He has got
Yes.
some fire alarm in his office. So probably he will not be, we can switch him. So
Yeah.
if Professor,
Our next speaker is ready. Is
Professor,
Professor
yeah,
V.V.
so
Raghavendra Sai. Yeah.
maybe we can ask Professor Sai to present and then we can take him at later
Yeah.
stage because he has a fire alarm in his office.
Yeah,
So,
yeah, got it.
yeah, okay, thank you.
So, Professor Shai, will you be ready to? Yeah. So that would be fantastic. That if you let me just give a small little bit time to introduce you, and we are very happy to have Professor V.V. Raghavendra Sai, who is currently the faculty member of Applied Mechanics of IIT Madras, and he is did his PhD in biomedical engineering from IIT Bombay in 2009. And his primary research work is biosensing technology for biodetections of biomarkers and pathogen. He spent 2 years postdoctoral fellowship at University of Idaho in USA. And he came back to India and joined IIT Madras from August 2011. So he has many publications and a very promising expert in the areas of biosensing. He also recipients of prestigious INE awards, the Epson Research Foundation in 2016. So with these introductions, I am very happy to invite Professor V.V. Raghavendra Sai to deliver his invited talk.
Good afternoon. It's pleasure to share the dais, the virtual dais with so many eminent researchers and especially T.K. Bhattacharya and my PhD guide, Professor Shomi Mukherjee at IIT Bombay, who is also present here. A good afternoon to all of you. And first of all, I would like to take this opportunity to thank the organizers to give me for giving me this opportunity to describe our work, showcase our work done in last about 8 years on this occasion. So I'll share my screen here. Okay, I'll share the screen, that's better. I hope you're able to see my screen now. Okay. Okay. The topic for today's discussion, I would say more of a discussion than a delivery of what we have done, is on human fiber optic biosensors. So this is something that I have been working on since my PhD days, and this has really been a favorite topic for myself, and also my students at IIT Madras have really enjoyed working on this topic. There are about 4 PhD students who have graduated from our lab, Biosensors lab at IIT Madras. So I'm going to present some of the work done by them, and then also show you some technology development. So as you all aware of point of care devices, we are very much aware of a glucometer and a pregnancy test kit. So of course, the working principles are different, but when a metabolite is there to be detected, it's somewhat easier because metabolite concentrations are typically in the higher range of concentrations in micromolar. Whereas when it comes to proteins, they are in nanomolar concentrations and even lower. So we do have these technologies, but we still have a lot more tests being done by conventional means, such as ELISA and CLIA. CLIA, known as chemiluminescence immunoassay. It's a replacement of laser technique, which is much faster. This CLIA is much more faster, and that's how the diagnostic technology is now completely CLIA only. But unfortunately, as you see, a lot of tests are being done using this very high-end technology. There's a lot of automation is involved in this technology, and that's how they are limited to central laboratory somewhere in major cities. But when it comes to diagnosis, many times we need quick diagnosis, and that's the reason we do need point of care devices. But some of the existing technologies, or all existing technologies in the market, somehow fail to reach the point. So what we want to do is we want to develop certain technologies that can be useful for not only diagnosis, water, food, and pharmacy, but many other applications in very particular applications like agriculture. So what we plan to do is, what we do in the lab is we make use of optical fibers and nanoparticles, noble metal nanoparticles, especially gold, as the tools to make devices. Basically, device development mainly for chemical and biosensing applications. And particularly, if we can make it for rural and resource poor conditions, that's great. So as you are aware of this lateral flow immunoassay technology, pregnancy test kit is one of the examples of the applications that are being in use. So many of these applications require mostly either yes or no. That's good. Then the technology is good. Or otherwise, the analyte concentrations are quite high. Then also this technology is good. But when it comes to quantification and non-specific binding, still there are problems. People are using it to an extent possible, and still this is only an indicator. A confirmatory test has to be done by using the gold standard techniques such as CLIA. So what we plan to do is, can we use some using something called as Evanescent Wave that appears at the core cladding interface and then exploit it for highly sensitive transduction applications. What one can do, one can realize is once a optical fiber cladding is removed and core is exposed, there is some evanescent field that is on the surface. But most of the times when you have a straight fiber, the depth of penetration is low. If you modify the fiber, you probably will be able to increase the depth of penetration as well as this field. So one such modification is typically this U-bend probe. Why U-bend probe is if you, for example, this is one of my examples I keep taking. If you are going on a straight road with a very high velocity and you are taking a U-turn, so what happens is you're almost at the outer shoulder, right? Where taking the turn. So in the same way, the light here actually, sorry. Excuse me. The light passing through this fiber, this is 200 micron fiber, as it passes through, so it takes actually almost appears at the outer curvature, and that's when you are forcing the light to be available at this outer edge, outer curvature in the U-bend region, and that's how you are improving the light matter interactions. So when you do that, what happens is, especially when you put some gold nanoparticles, over time you can actually see the nanoparticles binding, and that faithful reproduction of their spectral characteristics can be possible. So that's how you will be able to measure absorption property of any chromophore binding onto the fiber. For example, this is the gold nanoparticle characteristic. And one of the major advantages with this optical fiber is that, in fact, if you saturate the surface with the gold nanoparticles, you can actually get absorption of 4 to 5 watts. That means if you launch about 100 milliwatt of light, what you may end up milliwatt, let us say on the photodetector side, what you get is mostly one microwatt or few microwatts. So that's the amount of light that is taken up by these nanoparticles on the fiber surface. So this advantage can be exploited to develop plasmonic biosensors. So the label-free, this lateral flow assay typically has a sandwich immunoassay with gold nanoparticles. So with the simple setup, with the green light and it was price, we
Yeah.
program this is quite remarkable in my opinion. Why? Because
Actually, we can't hear you, Professor Rai. Your voice is not coming.
take home message here. My voice is not coming. Oh God.
It is
Now
okay.
Now it is okay. Yeah.
Okay.
Yeah, please.
Continue. So we just did some confirmatory experiments by doing over the gold nanoparticles. And those results indeed show that this system really works very nicely. The settings are like you just need 25 microliters of sample volume, 25 microliters of gold nanoparticle conjugate. Of course, the concentration of gold nanoparticles is quite high here. That's the only disadvantage. Otherwise, we are really able to get very nice response with the sensor setup. So we named this as a fiber optic absorbance sensor, biosensor, PFAB. And one greater advantage that I can say is one can actually change the nanoparticle size and modulate the dynamic range. So that's one of the major advantages with the system. Why? Because the clinical diagnostics really requires freedom with the operating range. So you typically need sometimes a narrow range or a wide range depending on the analyte of interest. So here you have that ability to simply choose a nanoparticle and have a dynamic range of interest. So we secure criteria. In fact, it's quite close. This technology or technique I would say right now is quite close to this assured criteria when the WHP point of care device. We compared these results with one of the first papers on attomolar and light detection published in Science in 2003. Of course, it's a 15 years ago. But it's still relevant, right? Because this biobarcode assay typically has a lot of amplification steps. To at least 5 to 6 steps are involved to reach 3 attomolar analyte sensitivity. Whereas here, using the PFAB, that can be achieved in 2 steps. One is an incubation step for 5 minutes. You mix the sample and reagent, keep it for 5 minutes, and then for next 10 minutes, you dip the probe and start measuring the rate. So that's the advantage with this. So we compared these results with the existing literature. We did find a promise with this technology. Sample volumes are low and no washing steps, no microfluidics, right? So these are the advantages. So with that, we thought, can we actually go further and do something, whether we can do some technology development. Before that, we thought we should try out the actual samples. So what we did is we tested this assay, this PFAB, with something called as lipoarabinomannan. It is a marker for TB diagnosis. Its LAM is present in urine. So we find that we were able to detect this amount from about 58 attomolar up to about 5 orders, 5 to 6 orders we are able to go. So that is the clinical relevant range. So we are now confident that this PFAB will be able to will be a good candidate for diagnosing pulmonary as well as extrapulmonary TB, and where the sputum sample is not available. The sputum or biopsy sample is typically required for cell culture and nucleic acid gold standard techniques. Here, such obligation is not there. Such constraints are not there. So we have also done some studies to detect lipopolysaccharides, LPS. These are endotoxins present on the cell wall of E. coli. We have kind of done a sandwich kind of assay. However, there is no biomolecule for as a receptor. It's a simple hydrophobic interactions. You have C18 carbon OTS, carbon chain OTS is present on the surface, and the hydrophobic portions of LPS interact with this C18 alkyl silane, and then they get trapped, and then we put polymyxine coated gold nanoparticles. So that really gave us again a good promising result. We were able to go down to 1 nanogram or 0.1 nanogram per ml of technique, LAL test. Around 2 grams of LPS, but it is only certain max variations. Because here, this has restrictions. So with that, we thought how this probes are somewhat expensive. Can we have an alternative? So then we looked at this polymeric optical fibers or plastic optical fibers. Many people have already done a lot of research on that before we started in 2013. In 2013, we thought we'll get some free samples from Mitsubishi Rayon chemical company, and then they gave us some samples and we did some experiments. So we actually had to, now we thought we'll make some U-bend probes, and this is how we made, we have come up with a simple technique of glass capillary based technique, and just thermal deformation of probes in a hot air oven, and a simple decladding steps by dipping in methyl acetate. So this is a simple process by which we are able to fabricate these POF U-bend probes. And then we indeed thought they can be alternative. We have characterized that we have taken 250, 500, 700, 750,000 micron fibers, and we did see what is the optimum shape, optimum probe geometry that can be a good candidate for these studies. So we found that this is one good study where we found a relation between what is the fiber diameter and what is the optimum bend diameter. It's around about 3 to 4 or about 2 to 4 is the bend ratio. So bend diameter by fiber diameter should be around that value, thrice typically. So, and then we also did immunoassays. We found that this 10 femtogram per ml maybe is possible. Then subsequently, we have studied some more work. We have done some more work on this plastic optical fiber, where we have tried to sputter gold on this fiber, even probe. And we found that by changing the deposition time, one can actually get LSPR properties with lower deposition time, and when we increase the deposition time, about 2 minutes, we got SPR characteristics. So these are the photographic images that you see now in the right bottom corner. So here we also have studied about their SCRS activity. We found that as quite satisfactory. But one surprising thing is, just like there are craters on moon surface, we also find craters on this optical fiber surface, plastic optical fiber surface as well. It's mainly because these fibers are made up of PMMA, and PMMA absorbs water. And what happens is, when you put it in high vacuum, so typically this absorbed water comes out, and there is it comes out as if it's bubbling out kind of. So as a result, you actually have such craters formed on the surface. Well, to an extent they are advantageous, but we have to do some more studies. So we have also developed some more plasmonic surfaces on silica as well as plastic optical fiber using seed mediated growth technique. So in the interest of time, I'm just skipping those. So we did find that these plastic optical fibers are actually much more stable in comparison to the silica optical fibers. Somehow the adhesion of these gold nanostructures is better with the plastic probes. So coming to technology development, here we thought, okay, we are able to go ahead with silica as well as plastic, but we find that these plastic optical fiber probes are less sensitive in comparison to silica probes. So at least the LODs are at least 10 to 100 times better in case of silica probes. So, and also handling silica probes is tough. So we thought as a part of Indo-German project, we have in fact developed this a bending machine for automated fabrication of U-bend probes. So manually we do fabrication with a candle flame or a butane flame like this, but we have developed a laser-based automated fiber bending machine where we have automated the above process, manual process. So we place the fiber here. This is the image, first image on the bottom row. So we place the fiber here, and then these arms are independently moving, but synchronously moving, right? So it goes like that. So and then you ultimately have these two arms coming closer to each other and getting bent through. So that's good, but still we take about a minute or two to fabricate one probe. So this is one of the major concerns, and we are actually working on improving the speed of the system currently. On the other side, when you want to develop a point of care device, you need a readout device, and you need a probe like this, which can be handy. And this is the kind of lab proof of concept of a probe cartridge that you see in the bottom right corner. So in the top right corner, you see the device. Here, this is the internal architecture of the device, where we have an LED and photodetector in this layer, and we have a probe holder mechanism here, and this is the probe cartridge. So this is the this is a real image of the cartridge, and this is the sample analyte. We call this as reagent, and this is the current device. It's a lab prototype that we have developed, and we wish to have something more sleek, aesthetic, as shown on the left side. We have partnered with the US company, and they have actually taken this concept for their applications. And I hope we'll be able to at least take this concept now towards commercialization. So not only that, these probes will actually allow us to build an array. So instead of one U-bend probe, you can actually have 8 of them in an array, and then you probably can have a mini CLIA. So whether this array fiber optic absorbance biosensor or RFAB, whether this can be an alternative to this existing technologies like CLIA for clinical diagnosis. So in this direction, we did make a fiber optic array biosensor, but this is, as of now, we find some coupling issues. Basically, this is 200 or 500 micron fibers. One has to really be concerned with the alignments of the source fibers and the detector fibers in this machine, so that one can actually have the probes loaded like this, and then you get a repeatable results. Okay. So one thing, when we developed this instrument, we had several bottlenecks. So some of them are like alignment issues, significantly alignment issues, and how do you hold these optical fibers, such thin optical fibers? We thought of magnetic coupling earlier, but nothing worked. So we actually went back to the traditional technique of using ferrules. So we are now trying to work on an alternative for this ferrules. So hopefully we'll succeed in next 1 year. So with that, we hope we are already have a proof of concept for tuberculosis. We hope we'll be able to do a troponin 1 test also, and see if this will be better than the existing LFA sensors. So other areas that we concentrate on pathogen detection and food monitoring. So I hope with that I made some sense of what we are doing here. And if you have any questions, please feel free to ask. Thank you very much for your attention.
Thank you, Professor, for your excellent talk. Now it is open for questions. So, yeah, I have a couple of questions. One, you mentioned about the gold nanoparticle decorated on the fiber, and there is a distribution of particle size. Is there any optimal size distribution for which you have found the best sensitivity for your analytic detections? Or
the surface cover, I can talk in terms of surface coverage.
Yeah.
My colleagues at IIT Bombay at that time during 2012, 2013, they have done a study where they have shown what is the optimal surface coverage.
Yeah,
So these studies have been published in Plasmonics in 2014.
Okay. So now, and second question that is coming, you said that the plastic one shows a few orders of magnitude less sensitive compared to silica. What is the problem actually in plastic? Why the sensitivity is such lower? What is the reason?
Yeah, so these optical fibers are made up of PMMA.
Yeah.
The major issues with the PMMA, we suspect that we are somehow not able to have active antibodies. I don't know whether there are no antibodies or less antibodies present, but we have difficulty in getting active antibodies that can give us a good response. So we are working on that. This is still an open problem, and nobody has really touched upon this problem so far.
Actually, that would be fantastic if you have a plastic one. Then cost-wise and as well as the robust for silica, it would be much manufacturability will be much easier then in that case.
Right.
So hope that you will in few years you will get the solutions. But it is a fantastic problem you are solving. Thank you. And if there is no other questions or any questions from anyone. Let us. Yes.
Can you check your chat box? If there are any questions, they will directly come to your chat box.
Yeah.
Okay.
One second.
Yeah, I don't have any.
I am not finding any. Sorry, anything in the chat box. Yeah.
Yeah, nothing.
So, thank you, Professor Raghavendra, and with that clap, of course, in the virtual platform, let me congratulate you for this nice talk.
Yeah.
And so now we will move on to our next speaker. Let me see that whether Manoj is ready or not.
Yeah. He has come back. He has sorted out the problem. So he's back. So maybe we can take his talk.
Yeah. So Manoj, so are you ready?
Yes, I'm here.
So Manoj, I have already introduced you. So I am just few lines. I would say that he is the most promising young scientist in this biosensing group, working for nearly 15 years in Icee in sense in this domain of molecular sensing. Optical-based sensing, I would say, is a very challenging task. So Manoj, with this, please, you are invited to give a talk. In the title of your talk is Single Molecule Sensing with Solid State Nanopores. Manoj, please go ahead.
Thank you, Professor Bhattacharya. I'm hoping that you're all able to see my screen.
Yes, you can see.
So first of all, thanks to the organizers for giving this opportunity to present work from our group. So let me go ahead and sort of provide the intention for this talk. So in this talk, I'm basically hoping to do two things. One is that nanopore sensing may be a slightly new topic for some of you. So I would like to give you an overview of nanopore-based sensing methods, and then follow it with what we are doing in our group to develop sensors using this method. So before doing all of these things, I would like to introduce my collaborators. So this is actually a team of people that we are working at Icee. And primarily the two students, Sohini and Ramkumar, have been the PhD students who have worked hard on this problem. We started this work about 5 years back when these two students joined as PhD students, and then they are graduated now, or they have submitted the thesis. So in their thesis, basically they have developed most of the things that I'm going to talk about today. And along with these students, we have a collaborative team. Professor Anjana Rao from USA, who is a biologist and who sort of introduced us and motivated us to work on this problem. Bharani Chakrabarti from chemical engineering, and then we worked a lot with DNA origami-based structures. And Akshay Naik, who works on measurement, low noise measurements and so on. And finally, Prabal Maitri from physics department. We do a lot of molecular dynamic simulations to understand our nanopore signals. So these are the collaborators that I have. And now let me go directly into the technical content of the talk, which is that let me first talk about what the nanopore sensor is. So if you look at this image, and let me just put my pointer. I hope this pointer is visible to you. So if you look at this image, then there's this chip here, and this chip contains a very small hole, right? And so this hole is the pore that I'm talking about, and this pore typically could be anywhere between a few nanometers, let's say about 4 to 5 nanometers, to anyway to as large as 100 nanometers. So it's typically 1 to 100 nanometer diameter pore, which forms the basis for nanopore sensors. And this pore is fabricated in a membrane. So this membrane that you see here, there are different materials that you can make. I'll come to that. Typically, the membrane size would be all the way from 2D materials like graphene, where it is a single atom thick. So all the way from single atom thick to, let's say, 50 nanometers, 10 to 50 nanometers thing. So that is basically the structure of this nanopore sensor. And then what happens is that as these sample targets go through, so for example, here there are some nanorods, but they could also be proteins or molecules, whatever they are, whatever your target is. So as the targets go through this pore, and the reason they go through the pore is because you're applying an electrical potential. So many of these species are charged in an ionic solution. So when you apply a potential difference, these things are going to migrate from one chamber to the other chamber through the nanopore. So the idea of nanopore sensor is that by measuring this ionic current and looking at the patterns of ionic current, can we identify what is passing through the nanopore? So can we identify this at single molecule level? So this has been one of the challenges or one of the goals in this community to use nanopore sensors. Now, before again I go into the particular class of nanopores I am working with, I would like to tell you that there are two types of nanopores. So one of them is this biological nanopore, and the idea here is that you use a protein. So you use naturally occurring protein, and these proteins have a pore in them. So there are various pore forming proteins, and those proteins are embedded in a lipid bilayer, as shown in this figure A. And so now what happens is that there is a pore that separates two membranes. So the lipid membrane separates two ionic chambers, one here and one here, and between them the molecules can get transported. So you can use this system, or what I work with in my group, what we do is to make solid state nanopores. So an example of a solid state nanopore is given here. So here what you do is that whatever the protein pore is doing, we try to mimic that in a solid state system. So in this example, for example, we have a silicon wafer. On top of this, there is a silicon nitride membrane, which has been etched. And on the silicon nitride membrane, we can make a nanopore using various methods. I will talk about that a little later. So in this situation, molecules can pass through this silicon nitride pore, and one can measure the ionic current using electronics, and then that forms the basis for sensing. Now, why were people interested in these nanopores beginning? So people started working with biological nanopores first, and the reason they went after this is primarily to do what is called as single molecule DNA sequencing. So the idea, so of course, I'm sure that many of you know that the standard sequencing methods, the way they work is that they chop the DNA into many pieces, Then they do PCR amplification, and then there are various techniques by which you can sequence based on termination, based on base addition, and so on. So these methods, the problem with these methods is that you require PCR to amplify the number of copies. And when you do that, a lot of base modifications. So for example, you may have a situation where the base cytosine is modified to methylated cytosine. So when you do the traditional sequencing, these modifications are lost because PCR does not preserve these modifications. So people wanted to do single molecule sequencing where you take a single strand of DNA and you should be able to read the sequences in that. So that was the motivation to do this. And on the right side here, I am showing a picture of a typical data that comes from such sequencing experiments. So as you can see, the different colors represents the different bases. And we are able to see that based on the ionic current magnitude. So what is plotted here is the, on the y-axis is the ionic current. So as you see that anytime a DNA base passes through, there's a dip in the ionic current because the base, the molecule is blocking the channel. So because there is a blockade, there's a reduction in the ionic current, and the magnitude of this reduction is dependent on the base, right? So the magnitude as well as the duration of the blockade. So there are two things here. One is you can look at the magnitude of the blockade. The other thing is you can look at the duration of the blockade. So
but
based on this,
is non-uniform with the base. Don't you think the blockade is non-uniform?
Yeah. I'm sorry. You said non-uniform?
Yes, yes.
Oh, okay. I mean, that's fine. I mean, there will be, so because we're dealing with single molecule, level information, there will be non-uniformity in the signal because of basic stochastic, so for example, conformation of the polymer as it passes through would change and so on. So you have to use some kind of a statistical approach to do the signal processing, but it is possible to distinguish bases as the DNA is passing through. In the case of biological nanopore. By the way, this is my data. I don't work with biological nanopores. I will come to my part later. But this is to show why the motivation for this biological nanopore, what people did. So they were able to do this. And today, the status of biological nanopore is such that there is a company called Oxford Nanopore Technologies, and I'm sure that there are probably some more who are actually commercialized this thing. They're actually selling systems where such sequencing, such single molecule sequencing is possible using biological nanopore. So it's come to a very mature state. The field of biological nanopore and single molecule DNA sequencing has come to a very mature state. Now, if you again, here's an example to show the maturity. So people have used this nanopores, for example, to track real-time mutations that are happening in the COVID, the virus relevant gene portions and things like that. So it's very mature then. So now compared to that, let me skip this. So compared to that, where are solid state nanopores today? I mean, why would you want to do something different compared to biological nanopores if they're already so mature? So first of all, let us see where they are today. So today, the problem with solid state nanopores is that people have not been able to do sequencing at all. And primarily, there are three fundamental challenges. One is the DNA speed control, because the DNA is passing through very rapidly, typically one base per microsecond. And the blockade currents that we're talking about are very, very small, of the order of a few hundred picoamperes. So to be able to measure such extremely small currents at this very high bandwidth, that has been a major challenge. So people have tried a lot to reduce the DNA speed or to control the speed in some manner. So that's been an open problem still. The other problem is the membrane thickness. And one of the ways in which, so the base-to-base separation of DNA is only about 0.3 nanometers. So if you have a membrane that is 10 nanometers or 20 nanometers, that means lots of bases are actually occupying your volume. So you're not able to measure a signal that is specific to a base. So the solution to that is to make this membrane very, very thin. And that is done in a protein nanopore because the pore is in a very, the smallest construction of the pore is in a very thin region of that order. But in the case of solid state membranes, that is very difficult. And as a result, people have looked at 2D materials. So for example, graphene, MOS2, and so on. So that's again an ongoing program to make very thin membranes of the order of the DNA base-to-base separation. And finally, what is required are ultra small pores, because the hydrodynamic radius or the volume, the rates of gyration of these DNA or these molecules that are passing through, that's of the order of a few nanometers. So typically, let's say about 4 nanometers or so. So if you have a pore that is 20 nanometers, you are not going to have enough discrimination between the open pore and the blocked pore. So ideally, you require a pore that is of the order of the molecular the size. So these are the three major challenges that are there in the case of solid-state nanopores. But given these challenges, why would anybody want to do this? Is that solid-state nanopores have these two unique advantages compared to biological nanopores. First is that you can make them over a very large spatial range. So for example, I can make a pore in a silicon nitride membrane, which is, let's say, 5 nanometers, all the way to 100 nanometers or 200 nanometers and so on. So I can go all the way from single molecule to a single virus in the same system. Now, this is something that biological nanopores cannot do, because the proteins that that form the protein that form the pores, they are always going to give you pores of the same order, a few nanometers. So you can't really tune that. So that is, tunability is something that biological nanopores are not going to have. And the second unique advantage of solid-state nanopores is that there are lots of new materials that are coming up with very different functionalities. So the solid-state nanopore system presents an opportunity to take advantage of these unique physics that is happening in these novel materials, exotic materials, and to come up with new construction schemes. So these are the two sort of very nice advantages which have also motivated us to work in this area. And so now focusing mainly on state nanopores, what are the materials, what are the methods, and so on. So as I said, people use graphene, MOS2, 2D materials like that to obtain very thin membranes. But silicon nitride has been a very conventional material, and the advantage is that it is integrated into the standard manufacturing. You can order it from foundries if you want. We can also deposit it in your own systems and things like that. So it's a very well-known material, easy to work with. And so what typically we do is to make a silicon nitride membrane, and there are multiple ways to make the nanopore. So the standard way is to use a high energy beam, like for example, a TEM beam or an SEM beam in an electron microscope, or you can use ion beam milling. So you can use various such milling methods to create the pore as shown in this figure, figure A. The other alternative which is catching up is to use dielectric breakdown. So the problem with this approach is that it's a fairly expensive method, and and so on. But here the advantage is that it's a very low cost, relatively low cost system. And what is done here is that you take the membrane. So you have to etch and create the membrane, but then you put the membrane in an electrolytic solution, and then you apply a relatively large voltage. And by large, I mean 10 to 100 in that order, not kilovolt level, but let's say 100 volts of that order. And then what happens is that the membrane breaks down because of various defects in the film, and as a result, you can make these very tiny pores. So people have made these systems where they continuously measure the current, and as soon as a pore is formed, you will start recording an ionic current, and immediately you stop the voltage pulse. So people have been able to make single nanopores of the size of the order of, let's say, a few nanometers, and they have also been able to make arrays of nanopores in this manner. So this is a method, the dielectric breakdown. It's called controlled dielectric breakdown. So this is a method that is catching up very quickly. And so the method that we follow is, of course, the conventional method shown in figure A. And in our lab, there are two major research activities that we have. One of it is in the direction of molecular dynamic simulations, shown in the figure, just a cartoon shown in figure A here. So what we do here is to try to understand the signal generation in these systems. So when a molecule passes through, what are the characteristics that we should look for? That is one part. And the second part is, of course, the actual fabrication and the building of the system, measurement, and so on. So these are two things that we do. So coming to how we fabricate that, it's a standard process. So typically we start with a silicon wafer, and we do low stress, we deposit a low stress silicon nitride membrane, because the membrane has to be, if there is stress, then the membranes can collapse and so on. So we do this LPCVD method of growing low stress film with about 200 nanometers. Then we etch it down. So we do a backside etch, and we basically create the membrane. And once we create the membrane, we do electron beam lithography on top of that. So we use the e-beam resist, and then we do e-beam patterning, followed by reactive ion etching. And this is basically our final chip. So our final chip will have the silicon nitride membrane over here, and this hole over here. And if you look at the what we have been able to do, we can make pore diameters all the way ranging from about 10 nanometers over here in the bottom right graph. So this is the nanopore diameter on the y-axis and the electron beam dose on the x-axis. So depending on the dose, we can tune the diameter of the pore from 10 nanometers all the way to about 40 to 50 nanometers. And we can make arrays of pores or a single pore and so on. And not only that, the distribution of the pore diameter, as you can see in this graph that I'm pointing to, the laser pointer, the distribution is fairly tight. So for example, in this graph, we are showing a pore with a nominal diameter of about 28 nanometers. And if you look at the distribution, that's fairly well controlled. 28 plus or minus 2, let's say plus or minus 2 or 3 nanometers. So we are able to get these pores in a very reasonably well-defined dimensions. And coming to the experimental system, what we do then, once we make this pore, what we do is that we fill. So there is a microfluidic holder that is, that can be 3D printed. So this is it can be 3D printed, or you can also make it in Teflon and materials like that. So basically a plastic holder, and in that the chip is placed. So the pointer is showing the chip there, and this entire assembly is put in a Faraday cage. And then we have some very low noise amplifier, which actually measures the ionic current. Because as I told you already, the ionic current is very, very small magnitude. So typically of the order of 100 picoamperes to a few nanoamperes. So we have to measure such very small currents. And there are specialized amplifiers that we use for that. And so here is a typical example of a signal. So in this top graph, you see just the buffer. So you don't see any, there's no feature here. But the moment you put something, so in this case, we are putting 5 nanometer diameter nanoparticles of gold nanoparticles, and you can immediately start seeing these spiky little things, these spikes that come in the ionic current. So these spikes are caused due to the motion of these single gold nanoparticles through the pore. Okay, so we can confirm that by various means. So I'll talk about that. So this is the kind of data that we can acquire from this system. So now going to actual measurements. So one of the first things that one does is to do this IV characteristics, and the IV characteristics gives you an independent measurement of the pore diameter, the D here. Right, so it just shows that the IV characteristics are consistent with what we measure with AFM and SEM and so on. So everything is fine. So now we initially tried to do some experiments where we could measure single particles. So in this case, we have single gold nanoparticles of 5 nanometer diameter. And what we did was to pass through that, right? So so this gold nanoparticle solution is in the cis chamber, and you apply a voltage, and they migrate to the trans chamber. And so one sees a lot of these spikes here. So in in all these three different graphs that I've shown, one sees a lot of features. Sometimes the spikes are up, sometimes they are down, and so on. So the question is that how do we know what is the signal? Because it looks very noisy. What does one understand from this? One approach that people have been trying recently is to use AI and ML and so on. But what we have done is to do direct simulations of this thing. We can do this process called as a Poisson-Nernst-Planck-Stokes simulation, the standard simulation that people do, to try to understand what is the electrodynamics of this. This is basically an electrohydrodynamic flow problem. And so one can solve that and find out what is the signal that we are supposed to get. And it turns out that the signal that we are supposed to get is like this. So the current is, this is the baseline current. So I'm showing the bottom graph, and followed by an up stroke and then a down stroke. So this is what we are supposed to get when a gold nanoparticle passes through the nanopore. So now we can go back to our experimental data and try to see whether our signal matches with that particular shape. So here is the simulation. The black curve is the simulation, and the blue curve is the actual measurement. And as you can see that there is some correspondence in the shape, okay, qualitatively. I mean, we can't really, because there are unknown parameters, so we can't really overlap them. But nevertheless, there is a qualitative corroboration between what we measure and what we compute. And therefore, we sort of conclude with some confidence that what we are measuring are actually single gold particles passing through the nanopore. Now, what we looked at, so as I already mentioned, one can look at the ionic current blockade, which is the magnitude of the ionic current that is blocked. Or you can look at the duration of the blockade, like how long was this blockade lasting. So we wanted to know which is better, like which gives us better sort of SNR, better discrimination between populations. So for some, so we found out that it's actually the blockade duration, the time, the dwell time as we call it, which was found to be very sensitive to the type of particle that we have. So for example, here is 5 nanometer data, and here is 10 nanometer data. As you can see, the dwell time goes all the way from 15 milliseconds to 25 milliseconds in this case, but the ionic current doesn't change that much. It changes only by, let's say, 30 to 40%. So then we wanted to look at it in a more systematic manner. So what we did was, of course, this is just showing that we can do 5 and 10 nanometers separately. I'm not going to talk much about that. But what we wanted to do was to understand how this dwell time would depend on the interaction of the pore with the target. Because ultimately, in order to use this pore as a sensor, the pore must be able to have a specific interaction with your target and some generic interaction with the other non-specific thing. So we wanted to understand how this dwell time will depend on the interaction. So in order to do that, we took a very simple system, which is that we take this gold nanoparticle, and typically in the system that we have, the gold nanoparticles are negatively charged. But what we did was to coat the nanoparticle with a polymer, which makes it positively charged. Now the pore, on the other hand, the silicon nitride pore, is always negatively charged. So now what will happen is that with our positively charged nanoparticle, there will be very strong electrostatic attraction. But with the negatively charged gold particle, there will be not that high electrostatic attraction between the pore and the target. And what we found is that, so here is these red and blue curve show you with different voltages, what is the dwell time distribution. So this is for the negatively charged particles, and this is for the positively charged particles. So as you can see, there's an order of magnitude difference. So this is like of the order of 0.1 milliseconds. So this is of the order of, let's say, 10 to 50 milliseconds. So by simply changing the charge on the particle, we were able to get orders of magnitude change in the dwell time. So we wanted to also understand this from a theoretical point of view. So we have done some work in terms of modeling that. I will not go too much into that. But just to suffice to say that our model that we have developed, the analytical model that we have developed, matches reasonably well with the experiment the experimental data. So again, it once again gives us the confidence that we are actually measuring the right thing. So the problem with the single molecule systems is that you get a lot of data because you're measuring every single event. As a result, you get an enormous amount of data, and so when you are flooded with data, you do not know what is the correct data, what is the good data versus bad data, what is the signal versus noise. So that's the reason we do extensive modeling and computation to verify that we are actually seeing what we think we are seeing. Right. So that part works well. So there is a reasonable agreement with the theory and the model, and I will just stop at that. But going beyond that, because ultimately you don't want to detect single particles, you want to detect molecules. So going to the single molecule detection, what we do is that we take the pore and we functionalize it biologically. So in this particular case, what we do is that we actually use DNA origami structures. So DNA origami is the technique by which you can make extended DNA structures, typically 100 nanometer size DNA structures. So basically what we make is a flat DNA plate. And on that DNA plate, we integrate aptamers. So in this particular case, we use an aptamer that is tuned to thrombin. So the aptamer will recognize thrombin, and the aptamer forms G quadruplex structures in the presence of thrombin. But if thrombin is not present, if it's some other molecule that is present, so in this case, streptavidin is present, they do not form this G quad structures. So we then try to understand what will happen in this experiment. And so what we noticed is that, so the first thing that we noticed is that this DNA origami aptamer structure that we are using, that forms the G quadruplex structure also in the presence of potassium ion. And it does not form in the presence of sodium ion. So in this case, when the aptamer is presented with potassium ion, we see these blockade events. Okay, and in the case of the sodium ion, we don't see anything at all. So that led us to believe that perhaps these events that we are seeing is actually due to the G quadruplex formation in the structure. Of course, it's very difficult to verify that, but this is our hypothesis. But another thing, so then we went ahead and did our experiments in this case where we have the DNA origami sitting on top of the nanopore, and the origami has aptamers on them. And when you look at the current, so here, for example, the yellow, oh, sorry. I'm sorry, I lost that slide. So here, the yellow distribution histogram. So this histogram is basically the distribution of all the events that we extract from our raw data, the ionic data. So the yellow is when only thrombin is passing through. Okay, so there is no aptamer. But the moment you put the thrombin with the origami and aptamer, we see that the yellow goes all the way to red. So that means that now the thrombin is not able to pass through that quickly. The dwell time is of the order of, let's say, about a millisecond here, but over here it's of the order of 100 milliseconds. So that means that the aptamer is basically binding to the thrombin and not letting it pass through easily, right? So as a result, it takes a lot more time. If you do not have the aptamer, if you only have the origami, then you get this blue distribution. And that blue distribution basically is basically interaction of the thrombin with this extended DNA nanostructure. So it just shows you that there is some interaction that the aptamer is presenting, which which can be discriminated. And when you put streptavidin, which is the non-specific thing, you do not observe that. So in this case, so for example, let's look at this bottom graph. You see that the purple distribution is from streptavidin, and the blue distribution is from the thrombin. So this is the ionic blockade, and you can see that the ionic blockade for thrombin is negative, whereas for streptavidin it is positive. So why does that happen? That happens again for the same reason that I mentioned, that the aptamer is specific to thrombin. So when the aptamer sees thrombin, it holds on to the thrombin. So thrombin is bound to the aptamer for an extended amount of time. And as a result, basically it hovers around the nanopore for more time, resulting in a more blockade. But on the other hand, if you look at something like streptavidin, which does not have a specific interaction, it simply goes through. So as a result, you don't have any blockade. In fact, we can show, I have not talked about that in this particular talk, we can show that you are supposed to get a positive, you're not supposed to get a blockade, but rather an enhancement, which people have also reported in other systems. So the point is that using the system, we are able to discriminate between a specific molecule and a non-specific molecule. Now, of course, this is very far away from actual application. So many of the talks that we have heard in the morning and in the afternoon, they have been focused on applications and so on. So this technology is very far from such applications yet. At the moment, we can only say that we have come to a state where we are able to fabricate these things, do some experiments, and that show promise in the single molecule level discrimination of proteins. But there is a long way to go before we can actually use it in real applications. Just as an additional data, I mean, one can also, so like what I showed you earlier is by extracting these ionic current blockades, these events from this long data. So extraction takes a lot of computation and so on. But if you don't want to do that, you can simply do a noise analysis. So in this particular case, we have simply plotted the noise spectrum, and we show that just the noise spectrum of this, or I don't want to call it noise spectrum, this fluctuation spectrum tells you about this thing. So for example, if you look at these different colors, these are for example, the purple one is thrombin and origami. So you see that the fluctuation spectrum can discriminate between specific binding versus non-specific binding. So with that, I will stop here. So just a summary of our work currently is that we have been able to fabricate these hybrid solid state nanopore structures. Hybrid because they have this silicon nitride inorganic framework. And on top of that, we are having these biological nanostructures. And together, these two structures give us the biological specificity. And currently, we are exploring this dwell time based sensing as a method to do single molecule level discrimination. And in the future, we hope to work on some real problems where we start to look at like diagnostic, the problems of diagnostic relevance. So that is where we want to do, where we want to go in the next couple of years. So with that, I will stop. Thank you for your attention, and I'll take questions if there are.
Thank you, Manoj, for excellent talk. I think now it is open for questions. So you can also chat. I can ask Professor Manoj to answer. So any questions from the audience? I am not finding anything in my chat box. So anyway, I have one question that is coming to my mind. It's an excellent work, but you are mentioning that you will be using, because truly the current is pretty low, so there is noise. You are say fluctuations and all, and you also try to incorporate AI-based or machine language techniques into it. So have you employed that one, or it is you are thinking?
Yeah, so we have not implemented that yet because we would like to. So we don't have that expertise right now. So we are looking for people who have that sort of experience and so on. So this is a very nice problem because also, as I mentioned, overall people are trying to implement such approaches because basically we are flooded with data. So in such a context, these AI-based methods would definitely be helpful. But right now we have not implemented yet. But this is something that we are actively looking forward to working with people.
No, I'm actually, especially, I'm very happy that you have taken the noise bundle. You say fluctuation bundle, and they have actually separate characteristics. So you might be able to get a lot of information from that.
That's true.
That you have correctly picked up the sense of it. So, any questions from the audience side? Otherwise, I will thank Professor Manoj.
Thank you, Professor
Thank you
Bhattacharya.
very much.
Thank you.
Thank you. So let me go to the. So the next speaker is ready. Professor.
Yeah, I'm ready.
Amit Jaiswal. So are you ready? Yeah. So let me just give you a small introductions of you. He's a very young researchers and a faculty members of IIT Mandi. It's an upcoming and one of the best I think I have visited that place. And he also selected as associate of the Indian Academy of Science, Bangalore in 2020. So he did his PhD from IIT Guwahati, and then he did his postdoctoral work with Washington University in St. Louis and also Technion, the Israel Institute of Technology, Haifa. And his main research is synthesis of nanomaterials for sensing, catalysis, drug delivery, and diagnostic applications. And he received the Department of Atomic Energy Young Scientist Research Award in 2017 and Mahe Young Scientist Award in 2018. So I invite Professor Jaiswal to deliver his invited talk on. The title of his talk is Sensing and Theranostic Application of Rattle-like Plasma Nanostructures. So, Professor Jaiswal, you are please proceed with your presentations. I can't hear you actually. So, sorry, it is muted.
It is muted. Jaiswal, can you unmute?
Please unmute. Jaiswal, you are still muted. Please unmute. Or you can again log in. So there is a problem. We can't hear you actually. So, and it shows that you are muted.
Hello?
Yeah.
Yeah. So now,
yeah. Now I can hear you. We can hear you. Please go ahead. Go ahead.
So are my slides visible?
Yeah, your slides are visible.
Okay. Yeah, so thank you, Professor, for a nice introduction. And I would like to also thank the organizer for giving me this opportunity to speak in front of you. So today I'm going to speak about interesting kind of nanostructure, what I call is a nano rattle. So my talk is going to be slightly different from the talks which you already have heard since morning, because my research work is mostly into synthesis of like nanostructures and looking forward with therapeutic and diagnostic application. So before going into that, I would like to introduce my institute. So I belongs to IIT Mandi, which is a very new IIT. Like recently we completed 10 years. And this is our south campus view in the daytime, and in the nighttime. It's a very beautiful campus. And this is the north campus of us.
So this is the only IIT probably where it snows. So you are most welcome to visit our institute. Yeah, once the pandemic gets over, obviously. So you will have a very, you can see this beautiful campus and can interact with the interesting like researchers present over here. So coming to my research work, so I basically synthesize different kinds of nanomaterial and look towards its application in drug delivery, bioimaging, catalysis, sensing, and environmental remediation. But my main focus in preparing interesting nanostructures. So today I'm going to talk about an interesting nanostructure called plasmonic nanораttles. But before going into that, I would like to speak a little bit about plasmon resonance. So we all know that metal contains electronic clouds. So if it gets perturbed by the irradiation with the electromagnetic wave, what happens is that this electron cloud gets perturbed from its equilibrium position, and we have a positively charged lattice and an electron cloud which is dispersed, and this can start by oscillating along with the incident electromagnetic field, which generates the plasmon resonance. So if it is an extended metal surface, so we get an extended surface plasmon resonance, you can see over here. And if it is a nanostructure, so what we can do is that we can localize this oscillation onto the surface of the nanostructure, and then what we get is a localized surface plasmon electron in which the dipole present on the surface of the nanoparticle oscillate along with the oscillation of the electric field of the incident electromagnetic wave. So so there is a particular wavelength at which this resonance occur, and we can tune this wave lambda max by changing the shape and the structure of the nanostructure. So if we look into the spherical nanoparticles, so it has got, like for example, this slide shows the SPR of silver nanostructures. The first figure shows for a spherical nanoparticle, it has around SPR at around 410 nanometer. But what happens when we change the shape from sphere to a cube? So what happens is that in case of sphere, the dipole was due to the symmetric shape of the nanostructure, that we can have only one kind of dipole. But when we create a cube, what happens is that the electron cloud tends to accumulate at the corners, extending the length of the dipole and thereby reducing the restoring force needed to keep it oscillating. And thus the energy shifts towards the red region, and we get a surface plasmon resonance peak at a higher wavelength as compared to the spherical nanoparticle. What happens if we keep changing the structure and increase the sharpness of the nanostructure? So when we prepare a tetrahedron, what we get is that the sharpness is increasing further, the electron will be moving apart. It will try to stay at the corners, and we see again a red shift in the SPR peak. Now, another interesting structure is a nanoshell, where you have a dielectric at the core and a thin metal shell around it. So in this case, what happens is that we get a further red shift in the SPR spectrum. Another kind of nanostructure is a nanorod, in which we can polarize the electron cloud in two ways. The first one is a longitudinal way, direction in which the electron cloud stays at this longitudinal axis of the nanostructure, and we see a longitudinal band. But we can also polarize the electron in the transverse direction. So in the transverse direction, since the charge separation is less, so the resonance occur at a higher energy. But in case of longitudinal electron oscillation, it happens at a lesser energy because of the larger, and we see a SPR peak at a more redder region. So the importance of these kind of surface plasmon peak is that we can use it for bioimaging as well as for photothermal therapy application, where we can use NIR light to heat up this particle, and can also be used for surge-based sensing application. So if you see this slide, so here what is demonstrated over here is that when two nanoparticles are close to each other, then it generates a electromagnetic hotspots at the junction of the two nanostructure. So when three are there, then you can see that the electric field intensity is intense at the junction. So this is again important, because if we put a Raman reporter molecule at this junction, so we can get a very enhanced Raman signal from this reporter molecule, which can be used for sensing application as well as for surge-based bioimaging application. Further, it gets heated up because of the impingement of the laser light or the light at which the resonance is occurring, and can be used for photothermal therapy applications. So coming to the structure which our group prepares is that we call it as a nano rattle. What we do is that we create a solid gold core and then coat that gold core with a silver shell. So what we get is that AU at AG kind of structure, where we have an octahedron solid gold core and then a cubic AG shell around it. And then what we do is that we again add gold solution into the nanostructure. Then due to the difference in the reduction potential, a galvanic replacement, a de-alloying process takes place, which yields a porous thin shell around the structure. So what we get is a kind of rattle-like structure with where we have a solid core encaged within a porous thin shell structure made up of gold only. So why are we interested in creating this kind of structure? So as we have started with a octahedral core which has a sharp tips, and now if this tip touches another metal surface, or if there is a space in between them, so that will be the sites of intense electric field, and that can be used for several applications. So what are the important properties of these structure which we get? Number one, we get a porous structure which can be used for loading of drug molecule inside it. Further, we can load a Raman reporter molecule so that it can be used for Raman imaging due to the presence of electromagnetic hotspot in these regions. Another very interesting property of this nanostructure is that the absorbance in the NIR region. So this NIR region has importance in biological application or therapeutic application because it has a higher penetration depth. So if you shine NIR laser light from outside, it can penetrate through skin or tissue till certain extent. And if a nanostructure is present inside the tissue, it can absorb that NIR light at its resonant frequency and can produce heat, which can be used to kill the cancer tissue. So this is the TEM image of the structure. So figure A demonstrates the AU at AG structure, where you can see the solid AU octahedron core surrounded by a cubic AG shell. Due to the difference in the density of this metal, you can see the contrast in the TEM image. And after galvanic replacement, you can clearly see the porous structure where you have a solid octahedral core inside and a thin porous shell outside it. So these are the sites where you can load the drug molecule or the Raman reporter molecule, and it can give enhanced SIR signal. So what we did is that we used this structure for dual imaging, Raman as well as fluorescence imaging, as well as for the delivery of drug molecule. So what we did, after synthesizing the nano rattles, we loaded a Raman reporter called BDT molecule inside this structure, and then we coated this structure with a solid silica shell so that this Raman reporter molecule doesn't come out of it. Next, what we did is that we coated this structure with a mesoporous silica shell so that in this mesoporous silica we can add certain drug molecules which can, and as a result this entire nanostructure can be used as a drug delivery vehicle. So due to the, you can see the TEM image of this structure, and due to this similarity to the iris of the eye, so we named it as nano iris. So here you can see the TEM and SEM image of the structure where you have the solid rattle, solid silica coated rattle, and then the mesoporous silica shell over here. So this slide demonstrates the SIRS performance of the structure. So when we performed the SIRS analysis, we saw that in compared to bulk BDT, we got enhanced signal of the BDT molecule from it, as well as that when the drug molecule doxorubicin is present in the mesoporous shell, we were able to get the fluorescence from those doxorubicin molecule loaded into the particle as well. We know that metal nanoparticle is a very good quencher, but because of the presence of the solid silica shell in between the nano rattle and the mesoporous shell, we were get the fluorescence from the dox as well. So this can be used for dual imaging, SIRS based imaging as fluorescence imaging of cells. So here this particular picture shows the SIRS imaging of the MCF7 cell line, which is a breast cancer cell line when once treated with this nanostructure, and we were able to do a SIRS mapping of these cells. And when we performed recorded the SIRS spectra, we got the peak for the BDT molecule. Further, the delivery of the drug doxorubicin, which was loaded onto the mesoporous shell, was checked through microscopy. The cells were the nuclei labeled with DAPI, and then the dox has its intrinsic fluorescence, which was monitored to understand whether the drug is being released from the cells or not, from the nanoparticles or not. So with increase in time of treatment, we see there is an increase in the fluorescence, which clearly demonstrates the dox loaded into the particle were released as well as taken up by the cells. So coming to the therapeutic potential of the nanostructure, we demonstrated that the nano iris itself in itself was non-toxic, But once we loaded the drug doxorubicin into it and treated the cell, we see there is a drastic decrease in the cell viability with increase in concentration of the nano iris. So we also try to understand the mechanism of treatment. So here the mechanism involved was like there was a generation of ROS which we monitored through flow cytometric analysis. We see with increase in concentration, there's a significant increase in the generation of ROS, which is reactive oxygen species, and there was no ROS generation when we use only the nano iris without any drug molecule. And here we show the AOEV staining, which again demonstrates the life and the dead cells. And the figure B shows the nuclear fragmentation, which is a result of with the treatment of doxorubicin molecule, which causes nuclear fragmentation. So we can clearly see the fragmented nuclei over here in the treated cells, and this is a non-treated cell where we can clearly see the nuclei labeled with the DAPI. Figure C shows the SEM image of normal cell line C1, and C2 is the treated cell line where you can clearly see the apoptotic body formation, indicating that the cell death was due to apoptosis induced by the doxorubicin molecule. So next what we did is that we tried to explore the stimuli responsive property of this nanostructure. As I mentioned that since they have the property of absorbing NIR light, so if you shine NIR light, what happens is that due to electron phonon coupling, heat is generated, and that heat can be used to kill the cancer cells through a process of photothermal therapy. So what we did is that we took this gold nanorattle, loaded a drug molecule doxorubicin inside the nanorattle using a phase change material called tetradecanal. Now this tetradecanal is a fatty alcohol which is a waxy solid at room temperature, but at higher temperature around 40 degrees Celsius it melts. So it transforms its phase from a waxy solid to a liquid state at around 40 degrees Celsius. So what we did is that we mixed this drug doxorubicin with this tetradecanal molecule and loaded into this nanorattle structure, and then further coated this nanostructure with the chitosan polymer in order to render biocompatibility and prepare a chitosan nanoparticle with this system. Now what happens is that when we shine NIR light onto this structure, the tetradecanal molecule which was loaded inside this nanorattle structure starts melting, and during this melting process it's released from the pores of the nanorattle. It also takes out drug from inside and release it into the surrounding, thereby causing the therapeutic effect. So here this slide shows the SEM image of the chitosan nanoparticle, which was having a core nanorattle. In the SEM image, we are not able to see the nanorattle, but if you see the TM image, you can see the nanorattle present inside the core of the chitosan nanoparticle. So here again we performed the SIRS imaging, because docs can also give SIRS signal. So the MCF7 cells were treated with this particle, and we were able to see the uptake of the nanostructure. Yeah. Hello. Yeah. So we were able to see the uptake of the nanostructure and the labeling using these nano rattles impregnated within a chitosan nanocarrier. So as I mentioned that this structure have a photothermal property. So here you can see that with increase in concentration, and if you shine a particular fixed amount of fixed intensity of laser light onto it for a 10 minutes duration, we can see an increase in the temperature of the particle. And further, these particles are photostable. So if we keep on switching on and switching off the light, we can achieve a rise in temperature. And once we switch off the laser light, it comes down to its normal temperature. And further, when we switch it on, it goes back, it increases its temperature and again goes down. So we can repeat it for several cycles. So this demonstrates the photostability of the nanostructure. So next we demonstrated the therapeutic potential. So here the green bar shows the control cells which were not treated with anything, and we can see the 100% cell viability. And here this particular bar shows the control cells with lasers to demonstrate that the laser itself is not any cell death, and we are achieving 100% cell viability. Now what happens to this particular 3 sets? So here these 3 sets demonstrate 3 different concentration of the nanostructures. The yellow bar nanorattles, which is loaded with doxorubicin along with the tetradecanal molecule. The blue one shows nanorattle without the drug molecule, and the red one shows nanorattle with the drug molecule plus laser. So as we can see that the yellow bar, when the drug is loaded inside the nanorattle, this is not showing any kind of significant cell death, which demonstrates that that the drug molecule is still inside the nanocarrier and is not released until and unless we shine laser onto it. The second bar, which is the blue bar, is blank nanorattle with laser. Once we shine laser onto this structure, obviously after treatment, so we see there's a decrease in the cell viability or increase in the cell death. This is because the heat generated by the nanostructure in itself can kill the cancer cells. So this is what is we called it as a photothermal therapy. So on the impingement of laser light, the heat produced is killing the cancer cells. But in the red bar, which is a drug-loaded nanostructure, and we are shining laser. So we are seeing a combined effect of drug as well as the heat, which is being produced from this nanostructure to kill the cancer cells. So we are achieving a chemophotothermal therapy using these nanostructure. Again, we demonstrated the mechanism of it. I will not go into that. Again, this is again a kind of cross generation and other ways. So the overall conclusion of this part is that the chitosan nanoparticle impregnated with the gold nanorattle can be taken up by the cell when we shine laser light from outside. We can do a SIRS-based bioimaging with this. We can achieve a stimuli responsive drug release, and which can show a combined chemophotothermal therapy in achieving cell death. So the previous structure which I was talking about was having absorbance in the NIR1 region. But we have, like it is known that NIR2 has a better penetration ability, and generally NIR2 is favored for photothermal therapy or photodynamic therapy application. So we thought of tuning the nanostructure in order to achieve absorption in the NIR2 region. So what we did is that instead of creating a cubic nanorattle, we prepared a rod-shaped nanorattle. We started with a AU bead structure, solid bead structure, and then grown a silver shell around it along the longitudinal direction, and then performed the galvanic replacement reaction using gold salt. And what we got is a rod-shaped capsular structure. We called it as nano capsule or nano beans. So here you can see that this figure demonstrates the NIR like the SPR absorption or the extinction spectra of the nanostructure. We see absorption both in the NIR1 and the NIR2 region. So this is the AU at AG, the parent structure which we use. It also has got absorption in both the NIR region. However, we cannot use it for photothermal therapy application because it is known that silver is toxic to cells. So what we did is that we performed a galvanic replacement reaction of these structure. So we prepared different sets of nanoparticle having different lengths, because we can tune again, like if we increase the size, we can shift the SPR peak more towards the redder region. So here we show the plasmonic nanocapsules of different sizes, and you can see that with increase in the aspect ratio, we are able to shift the absorbance in the NIR region. So here, this is the SEM image of the plasmonic nanocapsule at an intermediate step of galvanic replacement. And this is after the entire galvanic replacement. You can clearly see the porous structure. The nice pores at the edges is visible over here, which can again be used for loading of drug molecule to achieve a stimuli responsive therapy, or in itself, it can be used for photothermal therapy application. So we perform photothermal therapy application with this, and we see that this is again a photostable nanostructure, and with increase in the concentration as well as the laser power, we are achieved to increase. We were achieved to achieve a significant rise in the temperature, which can be used for cancer cell death. This is a very preliminary data which we used, which I have shown over here. That with increase in concentration of the nanostructure and shining of laser light, we are able to achieve a photothermal therapy with this nanostructure. So this work is currently under, we are performing it, and soon we will be completing it. So I'm not showing the other results from here. Again, like another interesting feature of this structure is the porosity present in this structure, which can be used for SIRS-based application. So here, this slide shows the SIRS performance of these nanostructure loaded with a Raman reporter molecule into it. And here the different set shows the different aspect ratios of the structure. So it is generally assumed that, it is generally known that if we increase the size of the nanostructure, there will be more electric field around it, and we will see a better increase in the Raman signal or a better SIRS performance. But here what we see is that the set 1 structure, which was the smallest amongst the others, that showed the highest SIRS performance. This is because here the shell is much closer to the solid core. So this is creating a much more intense electric field inside the nanostructure, or an intrinsic electromagnetic hotspot is created, which is giving rise to better SIRS performance compared to other structure. So this is the FDTD simulation data, where you can clearly see that the set 1 structure, which is the smallest structure, has a much intense electric field inside the structure as compared to the longer one. So this structure is the best amongst the set for SERS performance. So we took this structure and used it for SERS based sensing application. What we did is that we took a normal filter paper, lab filter paper Wattman number 1, and deposited that with these nanostructure. So here you can see the figure A shows the SEM image of bare filter paper, and B shows the filter paper loaded with this plasmonic nanocapsule. So here you can see that this is the blank filter paper, and after loading with the nanocapsule, it looks like grayish in color. And this was used as a flexible substrate, flexible SERS substrate, which can be used as a swab to detect any kind of trace molecule. So we used a Raman reporter over here, like 2 naphthalene thiol, in order to determine its performance, and we were able to detect concentration till 10 to the power minus 15 molar concentration. So here figure E shows the concentration dependent increase in the SERS intensity of the filter paper loaded with the nanostructure. Further, what we did is that we used this AU at AG nanostructure and prepared another kind of SERS substrate. What we did is that we took this polyolefin film and deposited this nanostructure onto this polyolefin film and heat it. So during heating, what happens is that this polyolefin film shrinks, bringing the nanostructure close to each other. So this again generates hot spot due to the closeness of the nanostructure and can be used as a SERS substrate for detection of trace molecule. So we use this as a trace molecule to detect pesticide on the surface of apple peel. We detected the pesticide called thiram onto that, and we were able to detect till the nanomolar region, which was like 1 ppb range. We were able to detect on the surface of the apple peel. So this is again an unpublished data, so I'm not showing all the things. So the conclusion is that this plasmonic nanorattle structure are very interesting because of the absorbance in the NI region, which can be used for photothermal therapy application. The porous structure can be used for loading drug and used as for delivery application, as well as the porosity can give us a better catalysis, which can be used for different kind of catalysis, which we have also demonstrated in case of like ORR reaction. It can also show peroxidase-like activity. Further, the intrinsic hotspot present within the nanostructure can be used for SERS sensing application as well as SERS bioimaging application. So with this, I would like to thank my group member who have worked hard to perform these experiments, my collaborator Tobia, who has performed the simulation part of the work, and Dr. Sri Kumar Kurungat for the catalysis experiment. Obviously, much thanks to the funding agency for generous funding for performing these experiments. Thank you.
Thank you, Professor Jayashal, for your excellent talk. Now it is open for questions. So from the audience,
yeah,
you can also.
Is there any chance of making the cell death selective using your nanораttles?
Selective, you mean to say selective killing of cells?
Yes, yes.
So yeah, that can be achieved. What we are doing is that we are now targeting breast cancer cell line. So we have coated this nanostructure with PEG, thiolated PEG carboxyl group and conjugated Herceptin molecule onto it. So this Herceptin molecule will bind only to the HER2 receptor present on breast cancer cell line, and we can achieve selectivity towards breast cancer cell line. So this work is underway. So hopefully within a few months we'll be able to complete this, and then I can show more data on in this.
Thank you.
Any more questions? Or I am not finding anything in the chat till now. So if there is no, I'd like to thank Professor Jayashal for this excellent talk. So thank you.
Thank you, sir.
Just 1 minute. Our next speaker is it's a oral presentation. Dr. Amrutaranjan Behra from Icee Bangalore. So, Professor Behra, you are ready to deliver your talk?
Yes, sir.
Yeah. So very nice that I will just let me see. 1 minute. Virtual platform is always, my God. Yeah, you share your, yeah. So.
Is my screen visible?
Yeah, your screen is visible. Perfect.
Yeah.
So you can start. Yeah.
Yes. Good afternoon, everyone. This is my talk is on in powder turmeric using visible and near spectroscopy, and this work is done along with my colleagues. There is an vision of Professor Shankar Kumar Selvaraj and Professor Rudra Pratap. We are from Center of Nanoscience and Engineering, Indian Institute of Science, Bangalore. Talk is as follows: introduction, and then bridging the gap. That is the difference between the state of the art, what is being done, and proposing. The principle based on which our approach is based. The details of our approach. There are some pictures and videos of the device prototype that we have developed. The details of sample preparation, measurement results, and conclusion. So the issue is adult. India, there is concern about adulteration in food and agriculture produce. In this talk, we are specially focusing on spices because these have a lot of commercial value, and India is known to be one of the largest exporters of spices to the world for a long time. And in this talk, we are focusing on turmeric, which is typically adulterated with spent turmeric. Spent turmeric is nothing but the remnant material after extraction of the curcuminoids, that is the 3 types of curcumin molecules that is present in turmeric, which is responsible for all its medicinal values. And this spent turmeric is usually mixed with turmeric to increase its volume and adulterate it. And we are proposing a on-the-spot decision-making system, a sensor which is handheld and it can be carried in your existing method for adulteration is by sending the samples to a lab, and this has its own problems such as limited accessibility. Not everyone has accessible to the labs, delayed decision making. The method is expensive, and lack of protocols for the evolving adulteration market. So as opposed to this, what we are proposing is a handheld device that fits in your pocket. You can get instant results from this. The price is affordable, and the models can be because it is based on AI/ML. The models can be improved online. So here is the basic principle. There is a light source. The light falls on the sample. So we do reflectance spectroscopy, and the signal that is generated, the spectrum, that represents the chemical makeup, chemical fingerprint of the sample. And so this is this present spectra, and there is this attribute which we want to measure. In this case, we want to measure. There are correlations among these, and for that we build machine learning algorithms. So there are in our approach. First part is training data collection, in which we use the device that we have reflect spectra. Same time, get reference to the
This NIR sensor, you bought it from the market? Hello? Did you buy this sensor from the market, NIR sensor?
See,
did you buy the NIR sensor from the market or developed it?
We have developed it, sir.
Okay, okay. Thank you.
In our lab. Hello.
Okay. Yes, yes. Fine. Go ahead.
Yes. So this is the device I'm talking about. The device we have developed. Internal components are some of them are imported, but characterization calibration that is done all in packaging of this device. And how it works. The field is for finding identifying different fields, not for turmeric, but the play the video is visible.
You are not audible, so please, Dr. Bera, we can't hear you.
Video right.
Now it is fine.
Video right now.
Okay.
Is played. I explain. Okay, I'll just playing the video, and then I'll continue the explanation. So yeah, it's coming. So that is the device we have in our lab, and that is what we have used for this study. So here are the details of sample preparation. We get turmeric samples, and then in the raw root form, these are dried, cut, and grinded to make it into powder form. And we also get the spent turmeric from one of the our industry partners, Universal Oleorigins in Kochi. And these powders are sieved with to keep the particle size consistent below 250 microns. And to mimic adulteration, we mix different proportions of turmeric and spent turmeric. And in this task, we have used 23 samples of varying concentration ranging from 0 to 100%. So 0 represents pure turmeric, and 100% represents adulterated the pure adulterant, that is spent turmeric. In the measurement, the different settings, which I'll just briefly explain. The averaging is the 35 times, that is before a spectra is taken internally, the device takes 35 scans and gives the average output. Integration time is optimized so that we have best signal to noise ratio, and the signal doesn't saturate. Light intensity is optimized accordingly. Calibration is done with respect to the white standard, which is barium sulfate powder, and dark signal is subtracted. This measurement is done in the range 400 to 1000 nanometers, and for each sample we collect 15 scans. There's reflected spectra collected from 4 samples are represented. The red one is 0%, that is pure turmeric, and 100% is the blue one, that is the pure adulterant. And in between we have 2 samples with 25% adulteration and 50% adulteration, and you can see that they trend in the reflected intensity. So what we do with this data, there can be 2 kinds of models that can be built for analyzing this data. One is classification, and the next is regression. Classification answers the questions whether the sample is adulterated or not, and regression answers the question the level of adulteration that is there. So initially we do a principal component analysis to see if the samples cluster out naturally, and we do see that beyond 20% adulteration, the samples are fairly clustered, and we should be able to classify them. So we go ahead and we use singular value decomposition for as a classification algorithm. We divide the all the samples we have into 2 groups. The first group A is less than 22%, and group B is greater than 22%. And in each group there are training set and test sets. Once we have trained the model, we using the training set, we apply that on these samples on the test set. And so this is the confusion matrix which represents this result. The x-axis represents the predicted class A and B, and this is the actual class. The diagonal elements actually shows the accurate prediction. Out of 75 total samples of A, 68 were correctly classified and 7 were wrongly classified as B. Whereas in case of sample B, we had 100% accuracy. And we saw that here there is 91% accuracy we could achieve. and the error results from the 20% adulterated, that is mostly on the boundary of, which is again usually observed in machine learning, and this accuracy is reasonable. Next, we go ahead with the building regression models to predict the amount of adulteration that is present. We again divide all the samples we have into two sets, training and test set, alternatively, and then we have used these 6 different algorithms to find the models, and these are the parameters, that is standard deviation and coefficient of determination from these 6 methods. And we find that the linear regression method here, we get lowest standard deviation and highest coefficient of determination. That is here. So we go ahead with this linear regression model and apply it to the test data that we have 11 samples. And so this is the known, the actual adulterated percentage versus the predicted values applied to the 11 samples. Remember that for each sample we had 15 scans. So the dots represent the mean predicted value, and the error bars represent the standard deviation that is achieved, and the solid line represents the x equal to y line, or the ideal case, and the dotted lines represent the boundary for the 15% error limit case. And we find that beyond for most of the samples, lower case of 0% 1%, the error margin is pretty much within 15%, which is reasonable. So the conclusions are, using a spent turmeric as an example adulterant, we could qualitatively identify adulteration blends beyond 20% concentration using principal component analysis. We had proposed a classification model using singular value decomposition method to distinguish samples with adulteration levels greater than more than 22%. We have tested 6 regression models, and we found linear regression to be the best, with a prediction error of less than 15%. This study shows potential identification and quantification of adulterants and pure turmeric samples, and this miniaturized spectrometer can be used along with chemometrics for identifying and estimating wide range of adulterants. And this paves the way for on-site quality analysis of agriculture produce. I thank this Universal Origin who has supplied us the spent turmeric samples, and our funding agency, Office of the Principal Scientific Advisor to the Government of India and Government of Karnataka for a grant support for this work. Thank you.
Thank you, Dr. Behra, for his talk. And now it is open for questions.
How do your results compare with the existing method of checking the turmeric?
So, sir, in this case, because we have adulterated with known values of spent turmeric, so the value, but we have used the same device for curcumin, measuring amount of curcumin in turmeric. The existing method is HPLC, that is high performance liquid chromatography method, and
Yes.
we have a reasonable accuracy there also. So within 80% accuracy, we are able to predict the amount of curcumin present. But in this case, this is analysis of which is already known because the samples are prepared by us.
I got it. Thank you.
Thank you, sir.
Unknown sample or adulteration, then how do you actually, when you cannot detect it, what kind of adulteration is there from the spectrum?
No, sir. Okay, it will be possible only if we do a training set, because it is machine learning based. In this case, this is specific to only spent turmeric. So if we train our data set with 5 different adulterants, only then we will be able to say which adulterant it is. Yes.
So in the current techniques, whatever you have mentioned, and then the techniques which you are going to propose, how does it going to be more cost effective? Have you make some analysis that why your technology will be preferred than the existing one?
Right now, sir, the samples are sent to these laboratories, NABL accredited labs for testing. And for testing, usually even when we have been doing for our reference, as our reference, it costs 1,000 to 1,500 rupees. This method what we are proposing, this is a handheld sensor, and you can use a mobile device to scan as many times, to measure as many times as possible. So it's a one-time cost for the device, but number of measurements you can do is virtually unlimited. So there's a cost reduction there.
What is the adulterant in turmeric usually? What do they mix?
So usually, okay, there are 5-6 adulterants like yellow soapstone powder. They mix metal in yellow, spent turmeric, which we have used in our work here. And there are these varieties of turmeric which are having very less amount of curcumin. That doesn't have any commercial value. They grind that and in the powder form, yes, makes sense. Chalk powder is also an adulterant in turmeric.
Okay, okay, thank you.
Dr. Bera, actually there are few chat questions, but I am not getting in my box. So if there is anyone wanted to ask any question, please do it, because somehow I am not getting any questions in my chat box.
Sure,
So,
sure, sir. I'll reply to.
Yeah. So yeah, if that comes to you, please reply.
Yes.
Is there any questions from the audience? Okay. If not, then we should thank Dr. Bera for this nice walk. So thank you.
Thank you, sir. Thank
you. So now I believe the session is over. So next, the speaker will be at 5 o'clock, I believe.
Yeah. Thank you, Professor Bhattacharya.
Thank you.
Thanks for sharing this. And I would also like to thank all the speakers, Professor Verma, Professor Raghavendra Sai, and Professor Amit Jaswal, as well as the last speaker who has presented from Icee, for a new method for detection. And I hope that all the participants, they have enjoyed. My request with the participant is that you have a method where you can go to the chat box and write the questions. So far, we are not receiving, and probably you can use that facility where we can become synchronous in terms of our presentation. So now we are breaking. We are going to have a poster session, which will be up to 5 o'clock. 5 to 5:30, we have a presentation from Professor Stewart Atchinson. He is from University of Toronto, and most likely he will be giving presentation which is a recorded one, and then we can have a question answer directly with him. Thank you very much. So we are going to close this session.
Okay. Thank you, Professor. So I will join at 5 o'clock, 5 minutes before 5.
Yeah, 5 o'clock. Thank you. Thanks.
अनम्यूट। ठीक है, शेयरिंग तो कर, इसको नीचे कर, क्या क्या ऑप्शन आ रहे हैं तुम देख लो। चल रहा है, आवाज आ रही है? अब देख, मेरे इसमें आ रही है, तुम्हें आ रही है? तुम्हारे साथ जो कनेक्टेड है उनको आ रही है? नहीं, उनको नहीं आ रही। क्यों नहीं आ रही भाई? क्या मैं ये ऑन कर रहा हूँ ना? पहले इसको म्यूट से ऑन करो। ये वो सही रहेगा। नहीं नहीं, तुम नहीं, मतलब तुम्हारा इसको इसके, हाँ इसको कर, पहले अनम्यूट कर अपने आप। मैंने अपने आप अनम्यूट कर दिया। हाँ ठीक है, तुम्हारी आवाज जा रही है, मतलब उन पे। मेरी आवाज नहीं है, पीपीटी की जानी चाहिए ना। वीडियो चला रहे हो तुम? वीडियो वीडियो नहीं है, पावर पॉइंट पे। तो पावर पॉइंट में वॉइस है तुम्हारी? हाँ हाँ, पावर पॉइंट में ऑडियो रिकॉर्डेड वॉइस है, तो वो स्लाइड वाइज होगी ना। हाँ तो पहले मुझे, अच्छा ये बंद करेगा, इसमें हटा, नॉर्मल सुना क्या है, नॉर्मल पीपीटी चला लो। ये है एक वीडियो है MP4। अगर वीडियो चलाएगा तो उसमें जाएगा कि पीपीटी और वीडियो ये जाएगी, ये इसमें आएगी वॉइस। वो तो पीपीटी है, पीपीटी में तो खाली पेजेस होते हैं ना, स्लाइड्स होती है। ये चलाएगा तो वॉइस आएगी। यार इसमें नॉर्मली वॉइस नहीं आ रही है, कल इसमें वॉइस आ रही थी,
तो
अभी
आपको अपनी पीपीटी चला के आवाज आ रही है संजय
हाँ, मेरे
सर?
कान में लाओ। ये तेरी एक
हेलो?
वीडियो है ना? हाँ, ये अभी तूने नॉर्मल इस पे चलाया है। तो इसमें तेरा वो कहाँ है? प्रॉब्लम क्या आ रही है? क्योंकि कल मैंने जब ये डाउनलोड करके चलाया था ना, कोई इसमें आवाज आ रही है।
हेलो?
ठीक है, इसमें आ रही है आवाज। ठीक है, अब तू चाहता है ये ऐसे शेयर हो वहाँ पे, है ना? इसे इसे यही चलने देना है। नहीं भाई, ऐसा भी रख सकता है कि इसको ये छोटे VLC में चलाएंगे ना, VLC में चलाएगा कोई दिक्कत नहीं, इसमें आवाज नहीं आ रही है। हाँ, इस वाले में नहीं आ रही, VLC से चला, VLC लेवल चलाती उसे ऑन करके रख, फिर नजर से कर रख। VLC पॉज कर दे, इसमें समझ गया तेरी बात। अब मैं शेयर कर दूँ एक बार। हाँ, एक सेकंड देख ही लेंगे, तो ये इसमें हम इसको नहीं इसको बंद कर, इसमें बंद कर। हॉल 6 में जाना है, हॉल 6 में ही था गया था, ये 3 क्या ही खुलेगा तेरे ख्याल? हाँ पहले तो सबको बंद कर। ओ एक टाइम पे एक ही चलता है, ये सारे बंद कर, मैं डायरेक्ट इसमें मैं बताता हूँ। नहीं नहीं ठीक है, 6 है ना तेरा? ये बंद कर, ये भी बंद कर, ये भी बंद कर, ये 6 है, ये 6 है ना। मामूली के भी ठीक है, ये तेरा आ गया, ज्वाइन करो। ठीक है, शेयर ऑप्शन है, ओके नहीं, ये तो वो शेयर, एक मिनट वो कर, बंद कर इसको। अगर मैं इससे जा रहा हूँ ना, हाँ उस वाले लिंक से खुलना पड़ेगा ना तुम्हें, तो ये मैं लिंक गया होगा, ये इससे जा रहा हूँ, ये खुल जा रहा है, एक मिनट में ओपन कर रहा हूँ, जैसे ओपन ये जा रहा है, वो उसका लॉन्च हो रखी है ना, बंद करना पड़ेगा, वो एक जगह चल कर, इसलिए ये बंद कर दो। हाँ अब अपना वाला खोलेगा, ये वाला ना। हाँ यहाँ से रुक जा, तेरे पे वो डाउनलोड नहीं किया हो ना तूने? नहीं नहीं, तो इसको हटा, वो नॉर्मल ब्राउज से कर, यहाँ से कर ब्राउज। अच्छा ये बंद कर दो एक बार दोबारा। नहीं नहीं, कभी यहीं से खोल लो, खुलेगा तो ये, यहाँ से ज्वाइन कर, फिर वही आएगा सेम। ये जो लेक्चर है ये हॉल 6, अच्छा हॉल 6 का भी तुम्हारा अभी खुलेगा ना 5 बजे, तब चलेगा। ये अभी तो तेरा नॉर्मल खुल के दिख रहा है, ज्वाइन फ्रॉम द ब्राउज़र, इसे कर, इसे ब्राउज कर, क्लिक कर, इसे कैंसिल करके क्लिक कर। आएगा भाई, लेकिन ओपन तभी होगा, बस चलेगा वीएलसी में, मुझे ध्यान है। ठीक है, वो जो शेयर आएगा ना, शेयर वाला ऑप्शन, और सब अभी वो इसलिए नहीं आ रहा क्योंकि हॉल 6 अभी स्टार्टिंग ही है। ठीक है, जैसे ये मेंबर्स तो ऐड हो रहे हैं, नहीं अभी वो शेयर का ऑप्शन भी आ रहा है, अभी में यही है और कोई नहीं है। हाँ ना, तो इसी में चाहिए जो शेयर तुम्हारा, वो लिंक दिया हुआ है ना शेयर का। ठीक है, मुझे बता ये जो लेक्चर है वो किसका है? अभी ये बाहर है, प्रोफेसर है नहीं? ठीक है, तो प्रोफेसर के पास जो लिंक गया होगा, इनवाइटेड स्पीकर है ना बेसिकली, प्री रिकॉर्डेड करके भेज दिया है, तो ये प्री रिकॉर्डिंग वहाँ पे चलाना है। आवाज आ रही है तो बोलेगा, तो आगे, लेकिन सामने वाले को सुनाई भी देना चाहिए ना। एग्जैक्टली, एक लगा ये नंबर स्टार्ट वीडियो, वीडियो स्टार्ट होना। ओ मैच आ जाएगा, ओके बंद कर, यू आर शेयरिंग रियल, बड़ी क्लास। हेलो
आपने
हेलो
पीपीटी चलाओ।
यार, मैं पीपीटी चला रहा हूँ, आ रही थी आवाज उसमें, मैं नहीं ना। भी आ रही है ये कुछ और को मैं कर दूंगा स्टॉप शेयरिंग है ये वाला स्टॉप कर दी तो पीपीटी शेयर कर पीपीटी खुली है नहीं खुली पहले पीपीटी खोल ले यहाँ जाए पहले पीपीटी ऑन कर ले अब शेयर में जा फर्स्ट पेज खोलना हाँ इसमें जा इधर हाँ शेयर कर पीपीटी अनम्यूट है ठीक है ये बड़ा कर यहाँ से बड़ा कर इसमें अब आ रही है सामने वाले से पूछूं वॉल्यूम तेज करो
पंत सर एग्जिट करो वापस
का स्टॉप हो रखा है दो चीज चला दी ना तुमने पीपीटी में भी आवाज आ रही है उसमें भी दोनों में आ रही है मतलब मेरे पास एक आ रही है बट ये
आवाज आ रही है
इसकी आवाज ही नहीं सुन रही कोई बोल रही है हेलो तेरी जो पीपीटी का स्लाइड है उसके अंदर बॉडी ऑडियो भी है हमारी आ रही है वो पीपीटी वाली आवाज हाँ बोलो स्लाइड ऐसे पहले शेयरिंग स्टॉप कर दे मैं बताता हूँ क्या प्रॉब्लम आ गया अरे दोबारा एक मिनट में उससे शेयर कर स्लाइड ये वाले पावर पॉइंट हाँ आप बताओ इसमें नहीं चेकिंग चल रही है अनम्यूट और यू आर शेयरिंग माइक्रो पॉइंट बस स्लाइड शो हुई एनिमेशन हाँ हाँ एक मिनट एनिमेशन हाँ स्लाइड शो पे जाना है हाँ ये आ रहा प्रेजेंट ऑनलाइन को हमें बोलना पड़ता है यहाँ पे उसे चलाना है ये हमें अगर सिर्फ चलाना है तो वीएलसी चला के छोड़ दे शेयर कर दे बस वो चलती रहेगी अरे फ्रॉम बिगिनिंग अच्छा फ्रॉम बिगिनिंग है वो यहाँ हाँ ये यहाँ पर ये चलाना है बस वो यहाँ से स्टार्ट हो जाएगा ये तुम्हें आवाज आ रही है चल रहा है उनका नहीं आ रही जब मेरे को पता नहीं आ रही तो मेरे को बता वीडियो ऑलरेडी वीएलसी में भी चल रहा है और इस पे भी चल रहा है लेकिन ये शेयर नहीं हो रहा है प्रॉपर समझ में आ गया बुला देखा मेरे को हेलो हाँ हाँ एक मिनट मुझे एक चीज बताइए ये जो पीपीटी है इसके अंदर ऑडियो रिकॉर्डेड है ऑलरेडी ओके नहीं नहीं हम अगर पीपीटी चलाएंगे तो ऑटोमेटिकली अगर उसमें वॉइस है वो भी उसमें चलेगा मतलब हमारे पास यहाँ पे दो हैं मतलब आप मेरे को ये बताइए आप किस वे में सुनना चाहते हैं तो मैं फिर क्योंकि हमारे पास वीडियो जो है या तो मैं पूरी वीडियो ही शेयर कर दूँ सो दैट कि वो वीएलसी में ऑटोमेटिकली जैसे एक मूवी चलती है जस्ट लाइक दैट वैसे ही चलती रहेगी हाँ बिल्कुल हाँ एग्जैक्टली वो हमारे पास दोनों ही है, वीडियो भी इनके पास है, ठीक है।
इनसे कुछ बात करते हैं ना टेक्निकल वाले में।
ओके हमें आवाज किसकी, आपकी? हाँ वो हमें भी आ रही है, जो हम चला रहे हैं वो हम तो सुन ही सकते हैं ना।
हाँ उससे बात करते हैं, 5 मिनट है।
हाँ हाँ हाँ।
हम्म, हम्म।
शेयर स्क्रीन, हाँ ऊपर एक और कर सकते हैं, बिल्कुल आप सही बता रहे हैं, ये ऊपर है एक शेयर वाला, हाँ नीचे करिए, एरो एरो पे क्लिक करो, हाँ नीचे करो, हाँ ये आ जाएगा शेयर कंटेंट, शेयर वेब ब्राउजर और शेयर माई मीटिंग विंडो, ठीक है। तो ये किसके साथ शेयर करना है? हाँ हाँ ये स्क्रीन शेयर करिए, आपको विजिबल, आप देखिए, आप इस सुनिए सुनिए सुनिए, आप इसमें ऐड है ना, इस मीटिंग में आपको विजिबल हो रखी है, अभी हमने ये स्लाइड शेयर, ये वीडियो शेयर करी भी।
और इनसे बात कर लेते हैं ना, 2 मिनट चल, बाद में बात करेंगे।
हम्म हम्म, ओके
क्या करेगा?
हाँ ठीक है, मैं इसको एक बार करता हूँ। मैं ये पूछ रहा था कि आप पीपीटी चलवाना चाहते हैं या वीडियो चला दें, मतलब दोनों ही ऑप्शन हमारे पास है। हम्म, वॉइस आप इसकी जा रही है, पीपीटी की तो आ ही नहीं रही। हाँ, exactly. पीपीटी की वॉइस आ रही है।
So motivation is, if you want to take a test to a remote community or a remote health lab, you need a small portable instrument. So a typical Good evening. My name is Stuart Aitchison from the Department of Electrical and Computer Engineering at the University of Toronto. This evening, I'd like to talk about some of the work we've been doing on the development of point-of-care diagnostics, and in particular, the use of photonic technology for creating fluorescent-based devices. So point-of-care technologies. So let's spend a moment considering what we mean by
Hello. Hello.
Hello. Yeah. Hello.
Professor Bhattacharya. Hello.
Yes. Yes.
Bhattacharya. Next speaker is not coming online, but his recorded message will be given. So maybe you can give a small introduction for him, and then we can display his recorded message.
And will there be any question answer session after that?
So he will be available. That is what he said, that he will be available. So any question coming, he will be ready to answer. So that is what I understand. Maybe he will join at the end because he has sent recorded message, recorded, lecture.
Yeah. Good. So here at the last lecture, I think, of this session, invited lecture 7. And it will be, the speaker is Professor Stuart. Hello. Professor Stuart Acheson, who is Professor of Department of Electrical and Computer Engineering, University of Toronto, Canada. Professor Stuart Acheson received a BSc and PhD from Department of Physics, Heriot-Watt University in Edinburgh in 1984 and 87 respectively. His PhD dissertation research was on optical bistability in semiconductor waveguides. From 1988 to 90, he was postdoctoral member of technical staff at Belcour, Red Bank, New Jersey. His research interests there were glasses and spatial optical solutions. He joined the University of Glasgow Department of Electronics and Electrical Engineering in 1990 and was promoted to the personal chair as Professor of Photonics in 1999. His research in Glasgow focused on the use of the half-band gap nonlinearity of semiconductors for the realization of all optical switching devices and the study of spatial soliton effects. And he is, from 2004 to 2007, he was the director of the Emerging Communication Technology Institute of the University of Toronto, where he established a 30 million open access facility for micro and nano fabrications. From 2007 and 12, he served as Vice Dean Research for the Faculty of Applied Science and Engineering, University of Toronto. Since 2013, he has been the Associate Scientific Director of Canada, India Network Center of Excellence. So he is, Professor Chushan is a fellow of the Royal Society of Canada and Royal Society of Edinburgh, a fellow of American Association for the Advancement of Science, a fellow of Optical Society of America, and fellow of IEEE and fellow of Institute of Physics. So our next lecture is by Professor Stuart Acheson, and the title of his talk is the photonics for point-of-care diagnostics. So let this deliberation be started. So you can turn on the video recording.
So point of care.
Yeah.
Spend a moment. Good evening. My name is Stuart Acheson from the Department of Electrical and Computer Engineering at the University of Toronto. This evening, I'd like to talk about some of the work we've been doing on the development of point-of-care diagnostics, and in particular, the use of photonic technology for creating fluorescent-based devices. So point-of-care technologies. So let's spend a moment considering what we mean by point-of-care technologies. In this paper by Madhu Pai's group from McGill University, they classified point-of-care technologies into 5 broad regions, ranging from at-home use, such as self-testing or pregnancy testing, through community use to clinical outposts, to peripheral labs to hospital testing. And point-of-care testing has applications in all, be it giving a more rapid result, allowing outpatient monitoring, or reducing the cost in hospital inpatient screening and monitoring. Now, what do we mean by point-of-care testing? They share some features in common. They provide rapid, typically around 15 minutes results, close to the patient, usually from a small, easily accessible excess sample, such as a stick of blood. They're particularly useful for monitoring the response to treatment, example of progression of HIV, mass screening in public health, or in emergency room and ICU units, where you can repeatedly use the test to monitor the progression of an infection, for example. So that's the definition of what we mean by point-of-care testing. So as an presentation this evening, we're going to talk about portable flow cytometry. And the first thing we'll talk about is cell-based assays for the detection of different cell populations. And we'll illustrate this with a CD4 counting example for monitoring and screening for HIV. We'll also talk a bit about immune assays, antigen, antibody detection, identification of dengue, and maybe some other work if we've got time. But flow cytometry has many applications. It can go through to DNA, nucleic acid testing, cell counting, cell sorting. This list can go on and on. So we're just going to talk probably about the first 2 this evening. So our motivation is, if you want to take a test to a remote community or a remote health lab, you need a small portable instrument. So a typical state-of-the-art flow cytometer is shown here. It's a large, bulky instrument, typically a few $100,000. It has computers, it's got reagents, it has a sophisticated support infrastructure, it requires training to operate. It's not really what you're going to take into a remote rural setting. Microfluidics is a good fit. It allows the use of low-cost disposable chips that could potentially be used with optics and photonics to produce a low-cost, easier-to-use version of the flow cytometer we see in this lab. And in this part, we're going to think about flow cytometer measurement for cells. And in this
Sorry, there is no voice.
Oh, yes, sir. I'm just.
There is some technical.
Yeah, there is some technical issue. They are trying to solve it. Let us see.
we're going to think about CD4 cells or T cells. And these cells are particularly important because they are part of the immune system. And with the onset of COVID, we've heard a lot about the immune system and how keeping a healthy immune system allows you to fight off diseases. And in particular for HIV, this is a real problem because, as illustrated in a very simplistic chart here, the virus enters the body. It destroys these T cells. So essentially, it infects and destroys those cells. And the problem there is the T cells, or the CD4 T cells, are your body's immune system. So essentially, HIV virus infects those cells, turns off the immune system, other pathogens to enter the body. So a particular test for monitoring would be to actually, can we count the number of those cells in a known volume? And one way of doing that is dyeing the cells with particular fluorophores. So these show schematically in the bottom right some cells, and they have CD4 sites, which means cluster of differentiation on the surface. And we can bind a fluorescently tagged antibody to those receptors, and that gives us essentially a labeled cell. It's a little more complicated because CD4, the T cells that we want also have other receptors on the surface, and the CD4 receptors that we want to count are present on other cells. So typically we do an absolute and relative measurement. We measure, for example, CD4 and CD8 or CD4 and CD3 as we do in this example. How does a flow cytometer work? In this chart, we show the operation principle of a bulk flow cytometer. Essentially, the blood sample, cells and beads and various things are injected into the top. They flow down this tube into this central region. There's a sheath flow of liquid that uses a hydrodynamic force to focus the cells into a single file. So as the cells pass through the focus of the laser beam, they flow in single file, one cell at a time. And they can flow 10,000 cells per second, and the laser can measure the forward scattering, the side scattering, and any fluorescent labels that are stained onto those cells. So you can get a lot of information about size, shape, fluorescent labels, proteins that have been bound to the surface and fluorescently labeled, for example. Miniaturize that device. Many groups have thought about this. Here's a couple of examples from the past. The one on the left is from Dongquan Lee's group, and it's essentially a molded PDMS chip, which is some electronics and a laser, which essentially counts a single cell at a time moving through a very narrow channel. The one on the right is slightly more sophisticated. There's optics integrated onto chips, so some light comes onto chip. There's a waveguide that focuses that onto the cell, and it can measure fluorescent signals, signals coming off the chip. The trouble with both of these approaches are they only have 1 or 2 cells per second. The channels are narrow, and we're only counting a single cell at the moment, at each instant. Now that doesn't work well compared with a flow cytometer that can do 10,000 cells per second. Here we're limited to just 1 or 2 cells. So it takes a long time to build up statistics and get a useful result. So how do we overcome that limitation of microfluidics? In our group, we've taken the approach of, well, we could make a very shallow channel that is wide and then use imaging. So here we show schematically a channel that has got cells, which are the circles with different fluorophores, red, blue, and green, and they flow through the channel. So if we make the channel shallow, i.e. only 1 or 2 cells deep, 10 to 20 microns, for example, we're not going to get a large volume of sample in the vertical direction, but we can make that chip wide. We could make it maybe a 500, 600 microns wide channel and still image that. And that would allow us to increase the throughputs while still allowing us to measure the fluorescent signals. The chip that we've got, the schematic on the left, shows a light source illuminating the chip and then a detector with some emission filters. So how we select different fluorophores is we take different wavelength selective filters and place them over different regions on the channel. So as we can see, as the liquid flows through the channel, it passes under the red filter, so we can only see the red fluorescent signal. And then it flows under the blue window, and we can only see the blue fluorescent signal. So we can count the cells with CD3 and CD4 on labels. Various prototypes, simple optical imaging systems. Here's some early examples from the lab. The one on the left is a very early example where we can see the workings. It's a relatively simple setup. There's an LED source in this case, the chip with an objective lens to image onto the camera, and then some emission filters. So perhaps not the best orientation, but a LED is going straight through, but if you've got enough emission filter, you can suppress the pump wavelength. Here's a slightly more sophisticated version where we illuminate from the top and measure from the top. Everything's put into a nice package in this example. We need to think about the sample processing because in this example, we're going to use blood as a sample, but we want to stain the cells. So we want to be able to take cells in a sample on a chip and stain them with the antibodies that we're interested in. So we looked at an active fluid control system. Here we've got a blister on the chip. This is the microfluidic chip shown in the bottom area here. There's an encoder and a linear actuator or stepper motor that will press on the blister. So as we press on the blister on the left-hand side, it'll create pressure and move the sample one way on the chip. And then if we release the actuator, it will let the blood flow in the other direction. So these are just a couple examples of the test. And if this works, we've got a small movie here which shows how the blood will move. So as we change the pressure, you can see the blood moves through the chip and back and forwards. So why do we want to do this? Well, on these regions here in the center, where are these plugs, these large circular structures, we're going to have some freeze-dried reagents. And we want to be able to stain the cells with the reagents we're interested in. And then that will allow us to count the fluorescently stained cell. So this simple approach, this was a test chip used to look at different amounts of mixing channels, the serpentine channels, and different numbers of reagent plugs in terms of how we could test the dissolving or we dissolve the dried reagents and the staining of the blood cells. So this turned out to be a very effective way of taking a dry reagent on a microfluidic chip so we could do all the processing at the same time. So working with a company, we were able to find a cartridge design that looks like this from the top. It's about the size of a microscope slide. There's a sample transfer port at the input, which is shown on the left. You can see the large blister circular structure towards the right. And then there are 3 windows in the center. The bottom 2 are actually where we add the reagents on plugs that snap into place. And then the central one is an optical detection window. So this slide shows how the actual detection chip works. We're now looking at the bottom side of that same chip. We load the sample in at the bottom, and you can see that's highlighted in red. The sample is then sealed The blister pump allows the blood to flow back and forward through the chip, as demonstrated previously. The reagents housed in these two circular channels on the left dissolve, and then finally the blood is pushed around to the detection window in the center of the sample. At that point, we illuminate it with a laser, and that causes the fluorescently labeled cells to emit. We have that under a microscope, and then what we actually see on the camera is this grainy flow. We don't need to image individual cells, but we see blue, green, and yellow dots, which correspond to some cells travel through one window, some through the other, and some through both. That would be CD3 labeled, CD4, or some cells are labeled both. The software actually puts a box around, color codes the bright spots, which are then counted. We know the dimensions of the chip. So what we want to find is the number of stained cells per microliter of sample. Final results. This is for a test instrument that we commercialized with a local company. We're able to do CD3, CD4 count in around 20 minutes with a whole finger prick of blood. Sample size is about 15 microliters, just a couple of drops of blood, similar to a glucose meter. Cell concentrations were in the range 50 to 1300 cells per microliter. Typically, a healthy person would be 600-700 cells per microliter. Once HIV infection progresses, that cell count number decreases, and the lower it is, the worse the immune system is responding, so the more treatment. The accuracy was about 10% in terms of the CV value for this particular test. Forward, can we use this portable flow cytometry system to do anything else? Can we actually do some of these more advanced immunoassays and maybe get a little bit extra information? And the vision is to have multiple chips, perhaps, that have different assays that fit into a single unit and can be selected. Maybe the blue chip does the CD4 counting, the red chip does the immunoassay for dengue or for sepsis, such as we highlight here. So how could that work? How could we use a similar approach to what we've just talked about to do maybe an immunoassay? Well, we use basically a bead array. So let's think about a target analyte. So perhaps we want to detect some pathogen or analyte that's floating around in a blood sample. So here we're just showing the molecules of interest as blue squares or diamonds floating around. So how could we actually capture them? We're going to use a bead. The bead will typically be about 5 microns across, similar size to a cell. That bead has been doped with a fluorescent dye, so it will emit if I excite it with a laser. And this particular example, I can have a dye APC, which will emit around 670 nanometers in the red. That bead is functionalized with antibodies, the Y structures. They capture the target molecules. So now I've got a bead, which is around the same size as a cell, that's managed to capture those target molecules. We like the beads because they've got a relatively large surface area. We can functionalize different amounts of antibody onto them and hence build our detection system. But how do we know how much antibody, how much pathogen has been captured? Well, we use a sandwich assay. We actually take another antibody, we flush through the chip, and this has got a PE labeled detection antibody. This yellow fluorophore will emit at 585 nanometers. And through this second binding, we have antibody, target molecule, antibody with a fluorescent dye. So now if we look at this system as a whole, we've got a bead that emits at 670 nanometers and a detection antibody that emits at 583 nanometers. So we've got a similar system to the one that we had previously. In principle, we could use the same type of structure, a microflow channel, with 2 different filters and measure two different beads. We could measure the presence of the bead and the presence of the detection fluorescent signal. It's slightly, we can make this a little more complex by realizing that the longer wavelength fluorescent signal, we can actually functionalize with different intensities. And how we do that is we could take some beads that have low intensity, that in this case capture the red target molecules, and medium intensity that capture the green molecules and a high intensity bead that captures the blue molecules. And if we are able to synthesize those beads and look at the number of counts, and this is on a flow cytometer from literature here, we can have different channels. So all the beads in this channel are measuring the red target molecule, all the beads here are measuring the green, and all the beads here are measuring the blue. So this way we can actually begin to multiplex more than a single detection molecule onto the beads. And this is why we use the term bead array. So it gets a bit more complicated. We actually move towards a prism type imaging system to actually allow us to look at those beads. So we have our bead, which we've just argued fluoresces at 2 different wavelengths. And we basically image this through a prism system with some filters onto our camera. Now, how does this work? Essentially, there we've got multiple emissions here. We've got the PE and the APC emission shown in the blue and the orange curve here. We use a couple of filters, which their positions are slightly different scales here, are shown here and here, to only look at the PE emission and to only look at the APC emission here. The filters have zero transmission in between, so that instead of giving us a very broad curve, if I just put these 2 spectra through a prism, I'll get one broad curve. But if I filter them and go through a prism, I end up with distinct dots. So each bead now appears in the camera as 2 dots. One in this case showing me a filter around 680 nanometers, one at 580 nanometers. So they're well separated. So if I measure the channel, the intensity of the long wavelength circled by red, that tells me what I'm looking at. And if I look closely, I've got some low intensity beads. And down here, I've got some high intensity spots on the right-hand side of the pair. And then I need to measure the channel, the intensity of the right-hand bead. And that tells me how much, the one shown in green, how much of the antibody or the target molecule has been soaked up by the bead. And if I play this, we can see here the bead pairs flowing through the cytometer. This was a deeper chip, so those in the center go a bit faster than the ones at the top and the bottom of the channel. But we can see clearly they're all, in this case, should have a similar relative intensity. This approach we can also extend. In this case, we actually showed 3 beads, 3 different beads with 3 different filters that we can resolve 3 different peaks in intensity. So it demonstrates the potential for multiplexing multiple samples together. So moving forward, what can we do with this? So this is a map of fever, and as you can see in the tropical areas, it's prevalent through South America, Africa, India, Indonesia. Though, if we look carefully, it's also in the US, Europe, and as the climate warms, the mosquito that carries the dengue is migrating further north and further south. So there are more and more infections spreading. So this is growing, and many mosquito-borne diseases are appearing in northern climates. In Toronto, somewhere in the Great Lakes area, we do see malaria and some of these mosquito-borne diseases, not only from patients returning from holiday, but community transfer diseases. So how do we measuring dengue? So what to detect? If we look, there are multiple things that you could particularly detect, and this just shows schematically time versus some of the different things. So the viral RNA is the virus present in the body. That's kind of hard to detect. The virus secretes an NS1, a non-structural protein shown in yellow, that peaks a few days after infection and then decays. And then we have IgM and IgG, the body's response to the infection. And this particular chart shows a second infection and the rates are changing again. So for example, if I measure the viral 1 RNA or the secreted NS1 protein, after several days, I might get a very low signal and get a false negative because the patient may have had the infection, be still suffering, but those levels have fallen. So it makes sense if I could measure multiple targets as a function of time and say, well, maybe the NS1 protein increases and decreases, then later on the IgG increases and decreases. This is all made more complicated by the fact that dengue has 4 different serotypes, so this graph is repeated 4 times for each of the dengue serotypes. So essentially, if you want to measure an NS1 protein and an IgG, for example, that would only work for 1 serotype, and then you'd have to repeat that for the other 4 measurements. So really you want to make 8 measurements. How have we done that? Well, we functionalized the beads. These are the 5 micron beads I mentioned. The APC barcoded bead, barcode 1, is functionalized with an IgG capture antibody. This IgG captures the NS1 non-structural protein. That in turn is the sandwich assay is then formed by the antihistine PE labeled antibody. So we get emission from the APC and emission from the PE dye. And then in the second medium intensity or lower intensity bead, we functionalize directly with the NS1 protein, which captures the IgG, which in turn is then functionalized with a fluorescently labeled PE labeled dye. So these are the 2 complexes we're going to look for our dengue detection. We started with spherotech bead arrays, and we used cytometer. These bead arrays are designed to get multiple channels, and we see at least for the channels P3, 4, 5, and 6, which are the standard channels from this bead array, and they're well defined, and they could be 4 different measurements. In our imaging system, we see slightly less well-defined peaks, but the evidence of the 4 peaks are still there. To improve the detectivity, we only used the P4 and P6 peaks. So we didn't use beads that had the P5 peaks. This gives us a better differentiation between the 2 signals and allows us to better quantify the 2 channels. We've got some image processing to do. So we've done some work essentially in MATLAB to basically load the images that come out of the camera that look like this. So kind of hard to see, but we can see the double dots for the beads. Then we do some thresholding and eliminate some the background, and then we do some binarization of the image, which is shown here, and we get a slight version of the image. Then we have some morphological operations that we apply, and we get still clearer image, and then we extract information, pixel position, intensity, etc. from the image. Again, all this is done in MATLAB. And then we look at the region of interest, and this could be because we've got the edges of the chips in this example. This is just really showing some of the issues that can go wrong. And from all that, we can define the mean intensities for the different points. And then we get different values. So each bead here is now being converted into a number. That is then read in, and that can be used to quantify the amount of fluorescence in each channel. One image, then we can replace that either for multiple image or a video. Turns out that it gets very computationally intensive if I'm doing a whole video. So what we ended up doing is actually stacking different images. So here's frame n-1 that we process. This is n-2 we process. So actually you can let the sample flow through the imaging region, take a snapshot, let more sample flow, take a snapshot, and quantify the beads within each of those regions. And we're able to do some calibration curves. Here's the flow cytometry calibration curve on the left, followed by the image analysis for the P6 peak, which is the NS1 immunoassay, and a reasonable fitting. These typical S-shaped curves indicate this is the region where it's most sensitive in the center. At the bottom end, it flattens off because we don't have enough samples, so we're not capturing enough of the fluorescently labeled target molecule, and on the top side it saturates because we've filled up all the binding sites on the beads. This just shows the P4 IgG immunoassay, and again we've got sample concentrations ranging from 0.01 up to 1 microgram. All these concentrations are typical values flowing around in a human blood sample. I'm going to skip this one because I'm running out of time, and then just skip on to some final results. These are flow cytometry data where we are looking here at 2,150 events on a scatter plot, looking at the different intensities. And then from our image analysis, each of these dots are one bead pair, and we can see they cluster into the 2 different regions. On the vertical axis is classification channels, so the higher intensity are for the NS1 beads, the lower intensity are the IgG beads, and then along the horizontal channel, we've got the detection intensity. So this position along here is the concentration. So the position of this ellipse the center of this ellipse tells me something about it. Another example with lower intensity, 0.01, we can see this LIPS has actually moved down to around 500. Detection intensity units is normalized here, and these are the and finally, across multiplexing, where we're using 0.1 micrograms per milliliter of NS1 and 1 microgram of IgG, again, we can see the two regions well defined in the green and the blue dots, and corresponding flow cytometry data. So this allows us to give us a reasonably fast approach to the presence of dengue markers. So with that, I'd like to finish some of the results with things we've learned about. Certainly in developing these type of tests, we really need to engage with stakeholders and figure out what the test will do, who will use it, and how it'll be worked. So we want to try and develop a simple test that can do some microfluidics and build a chip and an optical detection system that will allow you to make a real measurement. We've found product development takes much longer than expected. We need to take a multidisciplinary approach. We've worked with public health people, faculty of nursing, medics, electrical engineers, bio people, a whole range of different approaches. There's great opportunities for graduates and undergraduates to work, and photonics has a key role to play in developing this type of. I'd like to thank a large number of people, students are highlighted in bold, and postdocs, collaborators from University of Toronto, IISC in Bangalore, TCS, University of Stellenbosch, University of Strathclyde, etc., are all noted. So thank you for listening, and that concludes my talk. Unfortunately, I'm not with you this evening, but if you have questions and would like to learn more, please drop me an email at this address. Our recent work on the bead-based multiplex detection of dengue can be found in this Biomedical Optics Express that just came out a few weeks ago. There's also some more recent work on LED excitation of on-chip imaging flow cytometers at the IEEE Photonics Conference. So thank you for listening.
Thank you, Professor Achuchan, for his wonderful talk, a very well planned and articulated. And since there is no question, so you can actually send any questions to him directly through email. And I think this is the last lecture of these sessions. So I'd like to thank Professor Misro and all the participants on behalf of me.
So I thank Professor Bhattacharya and all the speakers who have given wonderful talk. And I hope that all the participants must have taken some message, some new, findings which has been presented. And this will go long way for their career. And with this, I would say that we will close the session for today. Tomorrow we'll start at the same time at 11 o'clock. Thank you very much.
Thank you, Professor Misra.